Hello and welcome. We are TaleForge, and in this lecture we'll focus on an overview of the ECS and the topics covered in upcoming videos. To begin with, let's introduce the subject of the ECS. As the name indicates, the ECS has three principal parts. Entity, which has neither behavior nor data. Instead, it identifies which pieces of data belong together. Component, which represent the data of your game or program. And system, which provides the logic that transfers the component data from its current state to its next state. So, in general, an entity component system architecture separates basic concepts. Entity is equal to identity. Components, which are data containers, and systems, which are responsible for behaviors. To visualize the process, take a look at the diagram. The system reads the local transfer components. Based on the logic contained in the system, it updates the local to word components, for example, moving from position X to Y. The system performs operations on all local transfers. The fact that entities A and B have in addition physics body and physics shape components has no effect on the system. However, you can configure the system by matching queries to require a specific component, for example physics body, or alternately to exclude entities with physics body components. Query will be discussed in the following videos. We would like to guide you step by step through the process of creating a 2D platformer game in Unity ECS, so that when this series is finished, you can show off your acquired skills and project in your portfolio. We would like to introduce you to the following topics: concept and basics, at which we will focus on issues relating to the IComponentData, IAspect, ISystem and SystemBase. We will explain what subscenes are and how they work, as well as the bake process and how authoring classes work. Also, an explanation of what archetypes and chunks are. Then we are going to show you transforms, especially moving, rotating and scaling. Also, non-uniform scale. Later, we'll move on to prefabs, where we will focus on instantiate prefabs and getting children. The next topic is dynamic buffer that will allow us to achieve least functionality in unmanaged code, of course with burst. The last issues in part 1 are JobSystem and EntityCommandBuffer. We will explain the parallel execution of the code in the ECS. In the second part, slightly more advanced issues, such as query, which allows us to perform operations only when components are available, and we also have the ability to refer to data. The next topic is scene management. We will focus on the possibility of changing scenes from within the systems. Also input, where we show you the management of input operations through ECS. Then physics, basic operations and slightly more advanced mechanisms based on physics shape and physics body custom components. The last topic is animations, handled through ECS systems. And more. In the project, I'm using Unity 2022.3.0 F1 and the following packages: entities and entities graphics version 1.0.16. First, we need to create a scene. I have already created mine and name it game. Then we need to create a subscene, which is responsible for converting game objects to entities. Let's name it Game ECS and save it. Since this is an editor bug that will most likely be fixed by Unity in the future, we can ignore this bug. Alright, let's move on to Writer and let's create bullet spawner component data. This is of course struct, as I explained in the short format video. Naturally, our struct inherits from IComponentData, so let's add it. So now, to implement randomness, we must reference the Unity mathematic namespace and create a random variable named instance. Let's just fix the namespace. Great. Now we need to create an aforeign class. This class inherits from monoBehavior and will help us to pass data to Baker. If we want to implement a pseudo-random system with a fixed seed, we need to create a seed variable. I assign the default value to 1 so that I don't have to change it in Unity editor. We need to add a public getter for the seed variable, so that it can be retrieved by the bullet spawner Baker class. Let's create bullet spawner Baker by inheriting from Baker and passing our class. Baker class allows us to convert data entered in the editor into data understood by the ECS architecture. Let's implement missing members. As you can see, there is a bake function with an aferring type parameter. There we can obtain an entity belonging to this class. We need to pass the none flag because we don't use the spawner's transform. Further details regarding transform usage flags will be covered in upcoming videos. Also, we want to include component data in the baking process to make it modifiable through aspect. We need to pass entity and create a new instance of the bullet spawner component data. I use object initializer to pass the instance parameter. As you can see, we can access the seed through aferring. Remember to include the Unity mathematics reference to get the random struct. Now we can see if it works in the editor. Let's create an empty game object called bullet spawner and add an aferring component. As we can see in the entity hierarchy, the component has been created and the random instance has been initialized. Everything works as expected. Let's go back to Writer and create the bullet spawner aspect struct. An aspect is a wrapper between component data and system. Aspects are useful for organizing component code and simplifying queries in your systems. Aspects must have read-only partial keywords. Now let's create a field for writing RW, which we will use to communicate with component data. In the aspect, we will write a function responsible for returning the random spawn position. Random position y equals to bullet spawner component data.value RW. We should use it to avoid impure struct copy. .instance, .nextFloat, and we can pass parameters like -10 to 10 and return new float 3, 0, random position y, 0. Now that we have our mediator, let's move on to implementing the system. We need to create a new file, bullet spawner system. Systems are responsible for executing logic. The system also has the need to add the partial keyword. It inherits from ISystem. There are 3 basic methods in the system: onCreate, onUpdate, and onDestroy. Let's look at the interface for details. OnCreate is equivalent to awake, onUpdate to update, and onDestroy is destroy in monoBehavior. Let's go back to bullet spawner system. We will be using bullet spawner component data, so let's add a line of code to the onCreate method, state.requireForUpdate bullet spawner component data. The system will not start its action, it update, until all required for update are met. Let's introduce a helper variable that will be used to check whether the system has already been started. Now we can retrieve the bullet spawner singleton entity using the System API's getSingletonEntity method. By having an entity, we can retrieve the bullet spawner aspect through the System API, which will be used to call the previously written getRandomSpawnPosition. Next, we'll create a for that runs 5 iterations to verify that the code actually works and that we get random values in the console. And of course, let's fix variable name from I to index. Okay, let's go back to Unity and set the seed on bullet spawner. Changing the seed immediately changes the state of the random instance via Baker. Let's run the game, and we got 5 random values. However, these values are the same at every game start. If you change the seed, the values are different, but it is still a result that is repeated every time you start the game. So it's no so random for us. So let's go back to IDE and get rid of the previous code in the bullet spawner offering. We can create the initial index of a random instance using system.random.next from 0 to int32.maxValue. Of course, next result is cast to uint. Now we can use the random.createFromIndex function in the bake method and pass the initial index. Okay, let's move on to aspect. Now, each time we use the getRandomPositionSpawn method, we randomize the index of the instance by calling random.createFromIndex function. This approach ensures that the numbers will be pseudo-random. Let's test the code in Unity. As we can see, each time we get a different instance, and the numbers vary between runs of the game. Well done! We implemented randomization in ECS. In the previous video, we saw how to create random values in Unity ECS. Today, we're going to use bullet spawner to instantiate actual sprite renderer entities. Let's dive in and see how it's done. As you can see, there are several important steps required for the graphics entities to work properly. If you are adding Unity ECS support to an existing project, remember that URP or HDRP is required. In addition, you need to add the entities graphics package. We did this in the previous video. Detailed step-by-step instructions can be found in the link in the description of the video. Our interest is to make sure we have SRP Batcher checked in the URP asset, since my project is on URP, and to make sure we have linear color space. Let's go to editor, click on the assets folder and universal render asset. We see that SRP Batcher is enabled. Okay, now select Edit, Project Settings, Player. In the Other settings, check if the color space is set to linear. If everything is put together correctly, let's create an object of type Sprite renderer in ECS game Subscene. We should see it on scene in the game view. Let's select background. In my case, it is an asset prepared by my graphic designer. Of course, it can be any asset you own or have downloaded from the Unity Asset Store. As you can see, I set texture type to sprite. This is required for the sprite renderer to work properly. Set the Z position to Psi1 in order to prevent Z fighting, and scale the X and Y values to 4. Then change the camera to orthographic and increase the size to 20. Okay, let's click play. Everything works. Fantastic. Now let's create bullet prefab. Right click in the hierarchy, to the object, sprites, square. Rename it to bullet and reset transform. And now let's go to assets, right click, create folder and name it prefabs. Drag and drop bullet to this folder. Now let's go into the prefab and replace the sprite in the sprite renderer with the asset we have. Alright, we are ready to start coding. Let's add two new fields to bullet spawner component data. One will be responsible for storing the number of objects we have to instantiate, and the other for storing the entity prefab. Let's also add support for new fields in bullet spawner Afferin and bullet spawner Baker. Add serialized fields and getters in Afferin. Now, in Baker, if you want to retrieve an entity from a game object, use the getEntity method. Pass a reference to a game object as the first parameter and specify transfer usage flags as the second parameter. In our case, we set the flag to dynamic because, according to the documentation, we want our object to be able to move at some point. 6 flags are available. The right choice of flags is important as it allows us to save resources on local transfer and local to word. Those of interest are none, just no transfer components. Renderable needs local to word to render the object, but doesn't need local transfer to move it in the runtime. Dynamic has local to word to render the object and local transfer to move it in the runtime. Okay, enough theory. Let's back to Rider and pass the second parameter, bullet count. And return to Unity. Delete this bullet prefab from scene. Then select bullet spawner and pass parameters. Great. All that remains is to add read-only access to our new fields in bullet spawner aspect, so we can read them in the system. In the system, we add the burst attribute, both to the class and to each method. This allows us to speed up the execution of our system. However, the important thing is that we can only use unmanaged code. This means that we are not allowed to reference classes, only structs. By default, each system executes in a simulation system group. According to the documentation, we can change the order of execution through the update before, update in group, and update after attributes. Furthermore, we can see that there are a number of groups that we can use to have our code execute before or after a given system. The three most important are initialization system group, updated at the end of the initialization phase, simulation system group, updated at the end of the update phase, and presentation system group, updated at the end of the pre-late update phase. In our case, running in default simulation system group is sufficient. So let's change the magic number to bullet count. Also, change the var type to float3 and of course add using via the rider's context action. Delete this debug log. Then, in order to create an entity, we need to refer to the state which has the information of the entity manager. Through the entity manager, we can use instantiate and pass bullet prefab entity. Before we return to editor, let's add a line of code responsible for setting the random position of the entities. State.EntityManager.setComponentData and pass entity as first parameter. Then local transform.FromPosition, random position as second parameter. Let's go back to Unity. Press play and we see that 1,000 representations of sprite renderers have appeared on the screen. Well done! Okay, let's add a random position in the x-axis as well. Go back to aspect and let's just duplicate the random position y line. Change it to random position x and pass to return value. Recompile. And we see that the whole screen has filled with bullets. Let's see the stats. About 200 frames per second. Great! In this video, we will focus on getting the bullets moving through the ECS system. We will learn how to do this using the entity query method. So let's dive in and learn more about the power of ECS. We want to be able to set parameters for each bullet prefab. With this in mind, we want to add a component to the prefab that will store such data. Let's go to Writer and create a new BulletComponentData class. I want the bullet to have three fields: float3 bullet direction, float3 bullet rotation, and float bullet speed. Then we need to create a authoring class. This class will be responsible for setting the necessary fields in the editor. So let's add fields that will correspond to fields from component data. And of course, let's add getters. Okay, let's jump into the Unity editor and set parameters. For our prefab, I set the direction of motion to the left, so x equals -1. I also rotate the visualization according to the direction of motion, so y is -180 degrees. And the speed of movement, say 5 units. Okay, let's create a Baker class that inherits from Baker bullet authoring and implement the bake method. Then get an entity. Transfer usage flags can be set to none. What I didn't say in the previous video is that when we instantiate prefabs, local transform and local to word components are automatically added regardless of our flag setting. According to documentation, an instantiate entity has the same components and component values as the prefab entity, minus the prefab tag component. In view of this, the transfer component becomes an ECS equivalent. So in the case of bullets, there is no need to set this flag. However, for bullet spawner, this is applicable since designating the flag as none for an object that already exists in the scene will omit the addition of local transfer, leading to micro-optimization. Now let's add the bullet component data via add component and just pass parameters. We want to use aspect to get data from system, so let's create bullet aspect. In bullet aspect, I need to add a read-only field that will point to our component data. And of course, getters. Now that we have the bullet aspect, we can extend the bullet spawner system class to set the rotation at spawn. Let's retrieve the aspect using System API. And let's create a new local transfer and assign to it the result of the local transfer.FromPositionRotation method. Pass two parameters, random position and quaternion.Euler bulletAspect.BulletRotation. Let's also specify the order of rotation. In our case, it is x, y, z. And set component data to new value. Great! Let's see if our bullets rotate. Hit play, and yeah, it does indeed work. Now we can create a class responsible for performing bullet movement. Let's name it Bullet Movement System. Of course, let's add onCreate, onUpdate, onDestroy methods and burst compile attribute. Also the update in group attribute with the simulation system group parameter, just for the sake of clarity. Okay, let's now add the require matching queries for update attribute. This attribute guarantees that onUpdate method will execute only if there is at least one matching query. It's time to build an entity query. Let's create a private variable and name it BulletEntityQuery. Then, inside the onCreate method, let's refer to the recently created field and assign to it the result of the query creation method. Let's write systemapi.queryBuilder.withAll bulletComponentData. Because we want to read all bullet component data. .withAll local transform to retrieve and modify position. .build. Let's disable bullet spawner for a while. Now add debug.log hi to onUpdate and check that everything is working as it should. As you can see, I can't see debug.log after turning off spawner. So let's remove the return. Hit play in Unity. And voila! Entity query is working correctly. Okay, delete this debug log and let's implement some movement logic. To retrieve data from entity query, let's introduce native array type. A native array exposes a buffer of native memory to manage code, allowing data to be shared between manage and native without marshalling costs. According to documentation, native arrays provide systems that allow them to be used safely with jobs and automatically track memory leaks. Let's create a local variable to hold an array of entities and an analogous array for local transfer. We are going to use allocator.temp. More about allocators in the next videos. We don't create a native array for bullet component data because we will use systemapi.getAspect to read the data in for loop. Okay, now let's cache delta time and create for loop in range from 0 to bulletEntities.length. Importantly, according to the documentation, the order of elements in native arrays is guaranteed. So you don't have to worry about pointing to the wrong element. So now let's cache bullet entity and bullet local transform. And let's get the aspect by calling systemapi.getAspect, passing the entity as a parameter. Now we can get the current position of the bullet by referring to bullet local transfer.position. Finally, we can calculate the new position. The new position is equal to the current position plus the speed of the bullet multiplied by the direction and the delta time. So, new local transform is equal to local transfer.fromPositionRotation with two parameters, new bullet position and bullet local transform.rotation. Let's not forget to set the local transform by calling state.entityManager.setComponentData, passing the entity and new local transform as parameters. Remember to call this pose for each native array. After all, we don't want any memory leaks. That's it. Let's go back to Unity and set the camera X position to -10 so we can see more of the bullets movement in the game view. Okay, let's play the game and check the stats. Performance for 2000 objects is still at a high level of about 200 frames per second. In this video, we are going to focus on making sure that our spawner is able to handle different types of prefabs. We will achieve this goal by using dynamic buffer. According to the documentation, a dynamic buffer component is a component that acts as a resizable array of unmanaged structs. As we can read, we have the length of the buffer, the capacity, and the pointer that indicates the data stored. In Baker, we can add a number of different buffers similar to component data. In the case of our game, we can dynamically change the list of prefabs at runtime in the future. So I implement the possibility to extend the functionality thanks to dynamic buffer. We could use BlobAsset, but it is definitely more difficult to implement correctly. And we are also close to the possibility of adding prefabs, for example, depending on the path the player takes in the game, or depending on progress. Okay, let's move on to Rider, specifically bullet spawner authoring. Let's add a field that stores a list of game objects, and a getter that allows reference from Baker. Now we can go back to Unity and create a bullet prefab variant. And don't worry, it's not Kang variant from Marvel. Right-click on Bullet, Create, Prefab Variant. Let's choose a variant and modify the sprite to say this element. Save the changes and move on to the ECS scene. Let's select Bullet Spawner and set bullet references in bullet prefabs. Then go back to the code and go to Bullet Spawner Component Data. In order to properly implement dynamic buffer, we need a struct that will store the prefab and, more importantly, will implement the iBuffer element data interface. Dynamic buffer only accepts structs that implement this interface and have unmanaged code. Also create a public field of type entity, bullet prefab. Let's remove the prefab field in the component data, we won't need it anymore. Now we are able to add a buffer in Baker through the add buffer bullet buffer element data. Let's rewrite our list into a buffer, creating new structs of type bullet buffer element data in for each loop. Adding to the buffer is similar to adding to the list. Of course, the past prefab parameters should be wrapped via getEntity. And let's remove bullet prefab from the parameters in component data. Since we added the buffer in the Baker, we also need to create a field in the aspect to inject dynamic buffer. So let's go to the bullet spawner aspect and add a private read-only dynamic buffer field. Now we can wrap instance randomization in the randomizeinstance method. Let's create a getRandomPrefab method that returns an entity. We will call randomizeinstance at the beginning, then get a random number from 0 to the length of the buffer. Now, just like with arrays, you can retrieve the prefab at the given index from the buffer. Great! All that's left to do is to make a fix in bullet spawner system. Let's change bullet spawner aspect.bulletPrefab to bullet spawner aspect.getRandomPrefab. And that's it! After all our efforts, let's go back to Unity, turn on the stats and hit play. As we can see, thousands of bullets with different visualizations are moving on the screen. Well done! Hello and welcome. In the previous video we added dynamic buffer support, which allowed us to differentiate between prefabs. Today I want to show you how to implement a job correctly, as well as how to set components via EntityCommandBuffer, pass parameters or query. You may ask, why use jobs in ECS code? First, you can use IJobEntity to iterate across component data when you have a data transformation that you want to use in multiple systems with different invocations. Second, to improve performance and delegate tasks to separate processor threads. Okay, so let's create public partial struct bullet movement job, which implements IJobEntity interface. Also create a private method, void execute, for now without parameters. In this method, we'll execute a piece of code. Depending on how we implement job, it will, for example, in our case, iterate over entity query elements. Depending on the problem, different approaches are possible. For example, you can pass native array to the job and call deallocate on job completion attribute, so it will automatically dispose native array after the job has finished. Okay, remove this line. Now let's add the code to the job that we ran earlier in the for loop. And of course, let's get rid of the loop here. This will cause some errors, but don't worry, we are going to fix them. In onUpdate, let's create a job using the new operator. Let's open the curly braces, leave space for the parameters, and finally call schedule. Okay, so what is next? As you can see, System API is not accessible from job. This is problematic, but makes sense for ECS behavior. Fine, let's pass the delta time parameter, and of course, we also need to add the delta time field to the job. To be able to set the local transfer component through job, you need to use EntityCommandBuffer, since state.entityManager is not available inside the job. You may ask, what is this? According to the documentation, an EntityCommandBuffer stores a queue of thread-safe commands which you can add to and later play back. You can use an ECB to schedule structural changes from jobs and perform changes on the main thread after the job's complete. In other words, EntityCommandBuffer allows you to set, add or remove components from within jobs, or create and destroy entities with the guarantee that they are thread safe. I think that structural changes also deserve a word of comment. Structural changes are operations that make Unity reorganize memory chunks or the contents of memory chunks. You can only execute them on the main thread and not from jobs, and they can require a lot of resources. The following operations are considered structural changes: creating or destroying an entity, adding or removing components, setting a shared component value. What is also important to know about the EntityCommandBuffer, it is recommended to use a different EntityCommandBuffer instance for every unique job. This is due to the possibility that if you reuse an EntityCommandBuffer in a series of jobs, the commands that the jobs record might be interleaved and the jobs might use an overlapping set of sort keys. For example, if both use chunk index in query. Okay, let's go back to Rider and create burst compile method private EntityCommandBuffer, get EntityCommandBuffer, ref, system state, state. Now, according to the documentation, for automatic playback and disposal of entity command buffers, we should cache entity command buffer system singleton and create a new command buffer. We want to execute the code at the end of the simulation group, so let's write ECB singleton equals get singleton and simulation entity command buffer system dot singleton. Of course, add required for update for this singleton. And return ECB singleton dot create command buffer with parameter state.wordUnmanaged. With this approach, there is no need to manually playback and dispose of the entity command buffer. There are quite a few entity command buffer system groups available. I have included a link to the documentation in the description of the video. Okay, let's create public entity command buffer field in the job. And of course, pass ECB parameter to job in onUpdate. Now let's change state.entityManager.setComponentData to ECB.setComponent. And also fix delta time name. Okay, but what about the rest of the parameters? The solution might be a proper implementation of entity query in job. Let's remove all calls related to native array. And pass entity query to job in schedule. Now we want to be able to dynamically retrieve the necessary parameters of each query element. How to do it? The solution is, of course, simple, however, requiring excellent knowledge of ECS. We can pass the parameters of interest, namely entity, local transfer, and bullet aspect in the execute method, but keep in mind the keyword in or ref. In allows reading, while ref allows read-write access. In the case of aspect, we don't pass any keyword. And now let's take a look at our entity query build. It is missing the information that we will be passing the aspect. With this in mind, we need to add dot with aspect, bullet aspect in the onCreate method. We could also remove dot with all bullet component data, we don't need it anymore. Let's check if everything is working in Unity. Great, we have implemented job. At the end, I want to show you a little bonus. Now, if we get ECB.asParallelWriter in our method, we'll be able to run schedule parallel and perform multi-threaded operation processing in job. Of course, fix the types for the ECB field to EntityCommandBuffer.ParallelWriter in the method and job. Also change public access to getEntityCommandBuffer to private. In addition, we need to add an int entity index in query with an attribute of the same name. This will allow us to retrieve a unique index, the index of each element in the entity query, which is necessary for ECB.ParallelWriter to work correctly. So pass a new field as a sort key parameter to ECB.setComponent. Okay, let's see if the changes work in Unity. Hit play and... Great! We implemented a job with multiply threads. Hello TaleForgers! In this video I will show you how implementing ECS can improve your performance. Of course, it's all thanks to the Burst compiler and jobs. However, the DOTS approach helps organize code and improve code management. Okay, so let's test some cases. To illustrate, I have increased the number of bullets to 20,000. The Unity Profiler is a tool you can use to get performance information about your application. You can connect it to devices on your network or devices connected to your machine to test how your application runs on your intended release platform. You can also run it in the editor to get an overview of resource allocation while you are developing your application. So how do we do performance analysis of our code? In Unity, we go to the Window, Analysis, Profiler tab. You can run the profiler as a separate process. This is very handy, so I will choose this option. Here we see the recording option. Leave it on. As we enable play in Unity, it will capture information about individual frames, which we will then analyze. Let's add micro-optimization. Change entity index in query to chunk index in query. It is a little bit faster in the case of ECB. I would like to thank Gradient of Games for his advice in the Reddit community. Okay, so press play in Unity and stop after a few frames. Let's go to the profiler. Let's select frame and analyze the system operation in Job tab. I expand the window with the mouse wheel. The whole difficulty is to find our job. This is much more difficult with many systems. Fortunately, I was able to track down the job without too much trouble. Click on the bullet movement job. On each thread, operations take about 1 millisecond. Okay, let's see what happens when we disable Burst Compiler. Remove all burst compile attributes, recompile, press play, and of course select correct frame. As you can see, all the results are still there because I didn't clear them. The results in Profiler are better than with Burst. Why? I read about this problem and, according to the documentation, you should disable native debug mode compilation, because enabling this mode makes all optimization disabled. I had this option enabled when I was debugging, so you might not be experiencing this problem as it is disabled by default. So let's go back to Unity, Jobs tab, Burst, Native Debug Mode Compilation. Of course, let's restore the burst compile attributes. Okay, now the expected result is better performance than if burst had not been used. Let's turn on the game and... Actually, we get about 2-3 times faster execution of the same code. Of course, multi-threaded. Fantastic. And that's what we mean by optimization. Okay, let's examine the situation where we abandon multi-threading in favor of a single thread. Modify or remove all ParallelWriter calls and delete chunk index in query. Also change schedule parallel to schedule. Go back to Unity, press play. Now you need to find a thread that bullet movement job is running on. As you can see, executing code on a single thread is slower than on multiple threads. I have put together a summary of all the results I received. It is immediately obvious that burst plus parallel jobs gives the best results. As you can see, using burst and single thread is apparently slower, but the result is a more stable game, 55 FPS. Without burst and with multi-threading, the result is worse, 52 FPS, therefore it is best to combine both techniques and get a stable 60 FPS. But it is definitely better than the first solution. It has no burst, no threads. 1 minute in Unity, Entity Query Refactor. In this short, I want to show you how long ECS code can be shortened with the power of jobs, entity query, and proper implementation. So let's dive in. As you can see, I'm using native arrays which are disposed in job at the end of execution. However, I can take advantage of the fact that an entity query can be passed to job to replace all native array calls inside the execute method. By passing entity query in schedule, I'm able to get element by element and execute the code. Of course, query must be built with the desired types. Now I can add more parameters to the execute method. It has in entity, in local transform, and bullet aspect. In means read-only access. The code works the same way, and there are a dozen or so lines less. Hello and welcome. In this video, we'll focus a bit on theory necessary to understand how ISystem and SystemBase work, and when to use which. So let's dive in and learn the interesting details. As I discussed in previous material, systems that implement the ISystem interface operate on unmanaged code. So we have no way to pass references, and almost everything is value-oriented. We have the ability to call methods analogous to mono behavior, namely onCreate, onUpdate, onDestroy, along with the methods available in the ISystem start-stop interface, namely onStartRunning equivalent to onEnable and onStopRunning equivalent to onDisable. As you may recall, ISystem could easily be tagged with burst compile attribute, which greatly improved performance. In addition, the ability to easily create entity query and the ability to limit the redundant work of the system are additional benefits. It is also possible to schedule a job. That's why in most cases, and probably for a few other reasons, it's a good idea to use ISystem practically whenever possible and limit the use of SystemBase. Okay, but what is SystemBase? Systems which implement the abstract class SystemBase are managed systems. It is possible to use references and additionally refer to the code called by monobehavior classes. This is a great advantage, but the use of managed types excludes the use of the burst compiler, which has a negative impact on performance, and this is something we would like to limit. Obviously, like ISystem, we can also use the onCreate, onUpdate, onDestroy, onStartRunning, and onStopRunning methods. In the case of SystemBase, we have EntityForEach, which allows us to iterate over component data. Such a call is very similar to using newer mechanisms like entity query. This is a convenient simplification, especially when we do the job only once in the code. According to the documentation, a maximum of 8 parameters can be passed this way. We have also job.with code, which executes a lambda expression as a single background job. In practically all cases, it is better to create a job as a separate struct and be able to reuse it for different cases. But if we are absolutely sure that the code will be used only once, then we can use this syntax. Okay, so let's move on to the comparison and the summary. Taking advantage of the fact that systems implementing the ISystem interface are structs and unmanaged code, we can use the burst compiler. Unfortunately, this is not possible in SystemBase due to the managed code. Both systems can use the idiomatic forEach, which is based on entity query. SystemBase can store managed data directly in system type. However, ISystem doesn't allocate the garbage collector, because we don't use objects, so no garbage is created in memory. It's a huge advantage. SystemBase supports inheritance, which can be a useful feature, but let's not forget that properly implemented interfaces can also greatly simplify code management. In the ISystem case, both ISystem and SystemBase allow you to schedule jobs implementing IJobEntity and IJobChunk. As I mentioned before, SystemBase has simplified syntax like entities for each and job with code. I think the comparisons represent the most important differences between the systems, which will give you an idea of what to use when. Whenever possible, use ISystem because of its high optimization and the possibility to use burst. If you need references or communication with mono behavior, for example UI or input, then SystemBase comes in handy. In the next long format video, we'll discuss the new input system needed to implement character movement. Of course, so that it can be applied to the ECS in some way. Hi, in today's material we will focus on the implementation of the new input system in ECS. The result is to simply display the debug.log in the console from within the ECS system. First, we go to the window, Package Manager. Of course, change it to Unity Registry. In the browser, we type input and select input system, install. We wait for the installation process to finish. In the dialog box, we click Yes to compile the backend. This will cause the editor to restart. After restart, let's create an input folder. We'll need it to store settings. A right mouse button, Create, Input Actions. Rename it to Input Controls. Select Asset and check Generate C# class. Then Apply. This will allow us to create and reference the Generate C# class from SystemBase. Let's see what the class looks like. As you can see, it's a pretty empty class with basic parameters like maps, control schemes, all cleared because we haven't added anything yet. So let's open the asset, click the plus next to action maps, and create the first map called player map. Here we will add our first action. It will be a horizontal movement, which means left and right. Jumping will be a separate action in the future. Let's rename the action to move. For the action type, we'll choose value, since a float value will be enough for us to move the character left or right. Let's set the control type to any, and remove the empty binding. Let's click on the plus sign and choose Add positive-negative binding. On the right side you can see what range of values will be accepted. In this case, -1 to 1. Let's assign the A key to negative and the D key to positive. Now save our asset or enable autosave. Okay, that's all here for now. Let's have a look at the input control script. As you can see, our player map has appeared in the maps, along with the assigned actions. We can see that the key information has appeared, as well as the player map actions track below. Inside the struct, 3 events of interest appeared: Start, Performed, and Cancelled. Perform will be used in the implementation of moving. In addition, a huge advantage of this system becomes apparent: the ability to listen for the occurrence of an event and, when it occurs, execute code. Okay, so let's move on to the programming part. But before we move on, I would like to invite you to support us on Patreon. Even a small contribution will help to develop the channel and the quality of the content present. Link in description. So let's continue. We will create the input system class which inherits from SystemBase. This system will be responsible for creating an input controls instance, enabling the input, and then creating a helper player input system that will manage the bindings found in the player map. Of course, implement necessary methods. So let's create a private input controls field. Then a protected onCreate method. Inside the method, let's assign input controls to new input controls. Let me remind you, input controls is our previously generated class. Next, let's enable the input by calling inputControls.enable. Now let's create the player input system class, which will also inherit from SystemBase. Importantly, we want to create this class from within the input system class. So let's add the disable auto creation attribute at the top. By default, all ECS systems are created at the beginning of the application. Now let's go back to the input system class. In the input system class, we add the var player input system equals entity manager dot word. This is important because we want to refer to the manage type dot create system manage player input system. Why are we doing this? Well, we want player input system to be unaware of the existence of input system and especially input controls and only manage the player map within it. Input system, on the other hand, is a kind of manager that knows about all children. Since we have a reference to a manage type, we can use a setter to set a reference to a player map in player input system. Let's go to player input system and add a private field inputControls.playerMapActions floor player map actions. Let's create a public method set player map actions, passing player map actions as a parameter. Inside the method, let's assign player map actions to the newly created field. What's next? We need to get to the movement we defined earlier. First, let's prepare a private void on movePerform method that takes the callback context from input action as a parameter. Now let's go back to set player map actions. Let's write player map actions.move.perform plus equal on movePerform. It is good practice to unsubscribe in the situation of destroying the system, so let's use the protected override method void on destroy. Let's copy the code responsible for subscribing, paste it into on destroy, and change plus equal to minus equal. Now go back to input system and call set player map actions. Pass inputControls.playerMap as parameter. The last thing we need to do is run debug.log in the onMovePerform method. Perform callback context.readValue float. Read value will allow us to read the value it as -1 or 1. Great, let's see if our newly created code works at all. Press play in Unity and alternate between the A and D keys. Voila! Everything was as expected. Hello TaleForgers! Today's material will focus on another highly anticipated topic, player movement in ECS. We will be combining events from the new input system with logic execute on the ECS side. Our goal is to move and rotate our sprite renderer depending on the input it receives. So let's dive in. First, let's turn off bullet spawner so that bullets don't interfere with our movement tests. Now let's create an object that represents an ECS player. The player will be a sprite renderer. In our case, it is a fox. Of course, we'll make it a prefab. We want to set the speed parameter through the editor, so let's create player component data and add float parameter speed. To execute the move, you need a container component that stores the direction in which the player should move. So let's create player movement component data, add new float parameter direction. This parameter will be set through player input system. Now we will create a player authoring class that will allow us to pass movement speed from monoBehavior to player component data. Of course, in player authoring we add a serialized field, while in Baker let's pass its value to the component. Also, don't forget to add the player movement component data component. Without it, none of our code will work properly. To organize our code, let's create a player aspect. Of course, we want to add ref_read_only field, player component data, and ref_read_write, player movement component data. Now let's add a getter for speed and a getter and setter for player movement component data. Okay, we are ready to implement missing logic in the player input system. Before we move on, I would like to invite you to support us on Patreon. Even a small contribution will help to develop the channel and the quality of the content present. Link in description. Let's move on to the player input system class. Let's create local variable movement direction and set it to read value float from callback. And update debug.log message. Then, via system API, get the player singleton entity. With the entity, we will be able to retrieve the player aspect and finally set the field. Also, let's add another callback, cancelled, which will reset the value of the variable in the absence of an input operation. Remember to subscribe to event in the set player map actions and unsubscribe on the onDestroy. That's it. Now that we have this field set up, what next? The most important thing is to create a system that is responsible for the movement of the player. We'll call it Player Movement System. A few things we need to prepare are: let's implement the ISystem interface, create the methods it as onCreate, onUpdate, and onDestroy. Add the burst compile attribute to maximize performance. We will also need an EntityCommandBuffer. I just copy it from bullet movement system. For a single operation, there is no point in adding a ParallelWriter. We just need a separate thread and job. Of course, add require for update for ECB. Next, we will create a player movement job. For now, we'll just create the ECB parameter. Since we are using IJobEntity, there is no need to create an entity query to get the data. However, you should specify in execute which parameters we need. In entity player, in local transform, and player aspect. In onUpdate, We'll create a new job, schedule it, and pass the ECB parameter. Since we want our movement to be frame independent, we also need the delta time parameter. Let's create a public field float delta time in the job, and in onUpdate, let's call systemapi.time.delta_time. We have everything we need to work, so let's focus on implementing the code in the job. First, we know that if the direction is set to 0, there is no movement, so we can create a condition to end the job earlier. Cache the position from player transform into a new variable. We are interested in left-right movement, so let's add the direction value to newPosition.x multiplied by the movement speed and delta time. Now let's set rotation. Quaternion new rotation equals player aspect.movement direction greater than 0. If yes, new quaternion with 1 on the y component. If not, new quaternion with zeros. Finally, set the component ecb.setComponent, pass player, and second parameter, new local transform, position equals new position, rotation equals new rotation, scale equals player transform.scale. We have performed all the necessary operations responsible for movement and rotation. I made a small but important mistake here. I wrote a quaternion with zeros, which means 0 element. If there is no rotation, I should write 0, 0, 0, 1. It as set x, y, z to 0 and the component w to 1, which means no rotation. In the next video, when I was recording the physics behavior, I noticed an error in the console. Assertion failed on expression is finite distance for sort, and I immediately understood what I was doing wrong here. Now it's time to test changes in the Unity editor. Press play, move player, and here we got an error. Let's see. Aha! We need to add player afferent to player prefab. So let's do it. If I press A or D key, we can see that the rotation has changed, but movement hasn't. We need to set the speed to, let's say, 5, and now the fox will move left or right. We also immediately notice that the camera is static, something we will have to deal with in the following videos. Hello TaleForgers! In today's video we will focus on the important topic of physics in ECS. We will use the knowledge we have gained so far and improve the code we have already written. So let's get started. Before we begin, a small piece of information. I updated Unity to the new version 2022.3.17 F1, so I eliminated the annoying editor errors when working on ECS. I prepared a simple scene, I changed the background to Winta and arranged the elements in the hierarchy. Empty game object that organize the structure. I have also created ground prefab that will be used to test Rigidbody in ECS. It is prefab composed of several modular assets. Today we will work in player and ground prefabs. And first we will set physics and collision, and in the second, collision only. I also changed camera to perspective for some in-game depth of view and adjust clip planes. First, before we start playing around with physics, we need to go to Package Manager and download the Unity Physics 1.0.16. Without this package, any change to entity physics will not be visible in the game. So let's wait for download process to finish. Now we want to import custom physics offering from samples tab. For ECS, when we are dealing with custom physics, we use the physics body component, which we can modify from the code. In the ground prefab, we just need to add physics shape, which is responsible for handling collisions. Of course, let's adjust the collision to the object, both size and center. Also set the bevel radius to 0.1 to round the edges a bit. Let's go into the player prefab and add two components, physics body and physics shape. For the physics body, we'll leave the motion type dynamic since we want our fox to move. We can add smoothing if we want more accurate results. For our purposes, I will skip setting this option. Set mass, let's say, to 10. The linear and angular damping can be left as they are. We can skip the initial velocity, but it might be useful for bullets later on. Gravity factor equals 1. We don't need a multiplier for gravity. Let's go to the Advanced tab and check Override Default Mass. We want to block rotation in the Z-axis, so let's set the Z inertia to infinity. Okay, let's move on to the physics shape. First, we want to adjust the size, center and bevel radius, just as we did in the ground prefab. Naturally, you can adjust the size according to your needs. Personally, I choose such parameters and I am satisfied with the effect of a soft overlap on the ground object. Let's see the result in the game. It looks good. Before we move on, I would like to invite you to support us on Patreon. Even a small contribution will help to develop the channel and the quality of the content present. Link in description. Okay, so let's go to the code. In the player movement job, let's modify execute method. First, add in physics velocity, player velocity parameter. We need it to modify actual velocity for player entity. And also add necessary using unity.physics. Now create two methods, setRotation and setVelocity. Remember to add best compile attribute. Let's add three parameters to setRotation: entity player, local transform, player aspect, and three parameters to set velocity: entity player, physics velocity, player aspect. Let's remove the code for calculating new position and set position to player transform.position. Then copy and paste the rotation code into the setRotation method. Of course, let's call in execute setRotation and setVelocity with the desired parameters. Now let's implement setVelocity method. Introduce new variable float3 velocity linear equals new float3 player aspect.speed multiply by player aspect.movement direction player velocity.linear.y player velocity.linear.z. Of course, set component via ECB, pass player entity and new physics velocity linear equals velocity linear. Let's clear delta time occurrences. Great! We implemented Rigidbody in ECS. Let's test it in the Unity editor. Press play, and as we can see, the player moves via velocity change. Hello TaleForges! In this video we'll learn about player jump in Unity ECS. Of course, we want to use physics to learn even more about ECS. So let's dive in and see how I implemented this feature. To handle the jump, we need to do three things. Listen for the action, assign a state, and depending on the state, handle the logic. First of all, let's add new action to input controls asset. Let's name it jump and select binding path to keyboard space. Don't forget to save asset. Okay, let's go to IDE and select the player input system script that we prepared in the previous lectures. Let's add handling for jump input in setPlayerMapActions. PlayerMapActions.jump.perform plus equal onJumpPerform. Create the necessary private void method with the input callback parameter. Don't forget to unsubscribe in the onDestroy method. Next, let's implement the logic in onJumpPerform. We need to get the player singleton entity to get the player aspect. And now we want to write player aspect.isJump equals true. We haven't created this field yet, but we will in a moment. Let's go to the player movement component data and create a new public bool field called isJump. Now change script to player aspect, add new property public bool isJump, get equals to player movement component data dot value read only dot isJump, set equals to player movement component data dot value read write dot isJump equals value. Great. Also, we need to store somewhere jump force value. So move to player component data and add a new public float field called jump force. Let's jump to player affering class, add serialized field jump force and getter. Then in Baker pass jump force to player component data. One last thing. Let's add a getter in player aspect to be able to retrieve jump force from the player movement system. Okay, let's implement jump logic. First of all, we want to refactor names, set rotation change to set player rotation, and set velocity to handle player move. Now we need to check if player is jumping, so let's write if player aspect is jump, handle jump, return. Of course, let's create a public void method and add two parameters, physics velocity, player velocity, and player aspect. Remember to add burstCompile attribute. Also pass parameters to handle jump. What is next? We need to apply impulse force to the player. So let's take a look at the documentation. Go to Methods tab and find Apply Linear Impulse. This one below, we don't need body scale. As you can see, to do linear impulse, we need to have ref physics velocity, which means read-write access, physics mass, and impulse force. Okay, let's back to the code and change the execute method's physics velocity parameter from in to ref. Also add the in physics mass parameter. Now pass ref player velocity and physics mass to handle jump method. Of course, change the parameters accordingly. In the handle jump, let's write player velocity.apply linear impulse. As you can see, it is from Unity physics extensions. And pass physics mass player aspect.jump force multiplied by math.up. Math.up is float free equivalent of the vector free.up. At the end, write player aspect.isJump equals false. Let's go to Unity, go to player prefab and set jump force to 75. Also set the rigidbody inertia on X and Y to infinity. This will prevent strange rotation behavior for the rigidbody. Okay, hit play and let's jump. As you can see, the jump works. However, we can also jump in the air, and that's something we will fix in the next video. Hello TaleForges. In this video we will learn how to check if player is grounded in Unity ECS. We will use collision word for collision detection and configure physics shapes. So let's see how to implement it. First of all, let's clean up the hierarchy, create new empty objects, level and systems. Of course, reorganize objects to desired parents. Go to the player prefab and select force unique in physics shape settings, because we want to make sure that there is only one instance of this particular collider. Let's modify the parameters. Center x equals minus 0.5 and y minus 0.1. Adjust scene window position a bit so I can see changes in the collider. Set size to, let's say, x equals 2.61, y 2.54. Bevel radius to 0.6. I think these parameters are fine for me. Friction mode to maximum. Also in the physics body component, set inertia tensor on x and y to infinity to prevent incorrect player rotations after jump or landing. Most importantly, let's add two physics categories: player 0 and ground 1. They are responsible for determining whenever is detection with desired layer or not. Player prefab belongs to player and collides with ground. Okay, let's go to ground prefab and add physics body. Set motion to static. Ground prefab belongs to ground and collides with player. Let's also add second ground instance and position it so we can test jumping later. Also position player to first platform or 2 seconds. I think it looks better in editor preview. Okay, let's write some code. Go to player movement component data and add a new field that will hold the grounded state. Public bool is grounded. Also, we need to add this field to player aspect with getter and setter, so we can modify state at the runtime. So move on to player movement system file, player movement job, execute method. Here we just want to add a condition check. If negation player aspect dot is grounded, return. Simple as that, because we want to block player movement during the jump. It's time to create player ground component data script, change to struct, and implement IComponentData. Then add public float free overlap detection offset. We want to detect collision with the ground, so we need to add offset to the player's center position. Of course, let's create the affering class, add serialized field, private float free, overlap detection offset, and also a getter. Next, we need to create a player ground baker class, implement baker interface, and bake method. Then let's get entity with transfer usage flags .none. Add player ground component data to this entity and pass necessary parameter, overlap detection offset. So now we want to implement player ground aspect. In this read-only partial struct, we need to declare ref read write player ground component data field to get offset. Create a getter, public float free, overlap detection offset, player ground component data dot value read only dot overlap detection offset. That's it. Let's move on to implementing the player ground system. Let's create new struct, add partial keyword, and implement ISystem. Also create onCreate, onUpdate, and onDestroy methods. Don't forget about burst compile attributes. This time we need to register our system to update in fixed step simulation system group due to physics operations. Okay, let's add require for update components, player ground component data and physics word singleton. We want to get current collision word from this singleton. Now let's implement ISystem start stop interface. So we can add onStart running and onStop running, which are equivalent of the onEnable and onDisable. Also add burst compile attributes and rearrange methods. OnStop running should be empty. In onStart running, add get singleton entity, player ground component data, then get aspect, player ground aspect. Let's create new float free variable, overlap detection offset, so we can read value in onStart running from player aspect. It's time to implement onUpdate. Let's write collision word equals system API dot get singleton physics word singleton dot collision word. Collision word implement overlap box method, which we want to handle in our code to detect if player is grounded. Next, create new partial struct player ground job. Remember to implement IJobEntity and add execute method. As always, add burst compile attribute. In the execute method parameters, let's add player aspect in physics collider and in local transform. IJobEntity creates a query that will retrieve the necessary parameters, and if entity with necessary parameters exists, then it will execute a job logic. We need to pass two parameters in order to implement ground check read-only collision word, and also read-only float-free overlap detection offset. Okay, back to onUpdate method. Let's pass collision word and overlap detection offset. Then schedule job. Let's implement the job logic, create a new native list, distance hit, hits, with allocator.tempJob, because we need to store all hit collisions somewhere. Okay, so we write isGrounded equals collision word.overlap box, pass player transfer.position plus overlap detection offset. It is center position of our box, new quaternion 0001, so no rotation, and field parameter is half extents, which we don't have, same as last parameter, collision filter. So let's enable unsafe code because we need to get pointer of the collider to get size and collision filter. Wait for Unity to apply changes. Go to project settings, player, over settings, allow unsafe code. Now create a new variable box collider equals box collider asterisk physics collider.collider pointer. We cast collider pointer to the box collider pointer so we can read the box size. As you can see, I got an error, so I have to add unsafe keyword to execute method. Also add the variable box geometry equals box collider arrow geometry. Because we are working with pointers, we need to use the arrow operator, not the dot operator. So back to our overlap box, pass box geometry.size divide by 2, because this parameter is half extents of the box. Next, pass a reference to hits, and as the last parameter, box collider arrow get collision filter, because we want the layers to be checked exactly the same way as for the player. One last thing, let's set the isGrounded flag to the state returned by the overlap box function. We can also add for debug purposes for each with debug.drawLine from player position to hit position with magenta color, duration equals 10 seconds. At the end, remember to dispose hits. So go back to Unity, recompile. Let's create new empty object playerGround and attach a playerGround offering component. Set offset to, let's say, 0 minus 0.2, 0. Also, you can create an empty object, name it physicsDebugDisplay, and attach a script with the same name. Check draw colliders, press play, and you can see colliders in game. It is a really great tool for debugging physics. Red color means dynamic rigid body motion, dynamic collider, while green means static rigid body, collider. You can even change state in runtime. Also, you can see magenta debug lines. Press spacebar multiply times to perform jump, and my system correctly detects if player is grounded, because I can't jump being in air. And that's what it is all about. Hello TaleForges! In today's material we'll cover the extremely important topic of animations in ECS. As of today, unfortunately, there is no official support for animations. However, with the help of a hybrid approach and managed components, I will show how to implement animations. The Unity Asset Store has great packages for ECS with bursts and job support for animations, which I highly recommend. Okay, so let's dive in and see how to implement animations in ECS. First, my graphic designer prepared 3 animations: idle, running, and jumping. All graphics are in PNG format. Of course, in the settings I choose Sprite, 2D and UI. Next, I prepared the animation clips I needed for the player animator controller. I created the clips by dragging the animation frames I was interested in. In the player animator controller, I created 3 states: idle, run, and jump. Let's start with jump. It is handled by the jump trigger and returns to idle after execution. The transition has the exit time option checked, but all other parameters are set to 0. Idle is combined with run. In both cases, exit time is disabled and transition duration is set to 0.25. I also added a parameter run, which I set from the ECS code and which allows me to switch between idle and run states. Here is conditions configuration. That's it on the animation side. Let's move on to the ECS scene and select player. Since there is no direct support for animation in ECS, the solution is to separate the visual part from the logic. With this in mind, I removed sprite renderer from player, so only physics body, physics shape and player offering left, and added the entire visual part, it as sprite renderer and animator, to the player visualization object, from which I create a prefab. This allows me to weld the visual object from the ECS code while leaving the logic object in the subscene. Alright, let's move on to the code. To implement the animation, we need a component with the player visualization and a component that stores the animator. Let's create a new class, player visualization component data, IComponentData, which will hold the game object player visualization. Since it is a class, we are dealing with the managed type. Similarly, let's create a player animation component data class that implements the ICleanupComponentData interface. The component labeled cleanup is not destroyed when the entity is destroyed, so it requires manual removal. In case the player entity is destroyed, I want to make sure that its visualization is also destroyed, which I will handle in the player animation cleanup system. Now let's add serialized field and a getter with the player visualization to player offering. Then let's add component object and pass the game object player visualization in Baker. This will allow us to spawn the player visualization from within the ISystem. Let's go back to Unity. Let's go to the player prefab and pass player visualization to the player model. Earlier, I created a basic implementation of player visualization system, which we can develop in the material. So let's add a player entity query field, and then in the onCreate method, write player entity query equals to systemapi.queryBuilder with all player visualization component data, because we want to retrieve the player visualization component we added to the scene via Baker, and with none player animation component data, because we want to block repeated execution of this system once player animation has been respawned. Don't forget to call build. Now add state.requireForUpdate player entity query, so that onUpdate is only called when the query conditions are met. In onUpdate, let's retrieve the entity and player visualization component data, Let's create the visualization via object.instantiate player visualization component data .player visualization. Now we can add the player animation component data component via EntityCommandBuffer. So let's copy the method from player movement system and paste it into the visualization system. Of course, add require for update for ECB. In onUpdate, write ECB equals get EntityCommandBuffer ref state. Then ECB add component player entity new player animation component data and pass the animator, which we will retrieve from the newly created game object via getComponent. Okay, we have our player visualization on scene. Well done! Now it is time for the animation system. Here too, I have prepared the basic structure of the system in order to focus on the specifics. Importantly, we update the system in the simulation group, order equals first, so that the ISJump change in the player movement system will be registered and we will get the correct, updated ISJump state at the start of the next frame, and before the player movement system is executed. In onCreate, let's create an entity query. We will need local transform to synchronize position, rotation and scale, player movement component data to read whether movement is occurring, and player animation component data. Of course, add state.require for update. So let's get these parameters in onUpdate by referring to entity query and get singleton. Catch transform from player visualization via animator.transform. Transform.position equals to player local transform.position. Transform rotation equals to player local transform.rotation. Let's cache uniform scale from player local transform.scale. Transform.scale equals to new vector 3 scale. And now we want to handle two checks. The first one where we check whether the player is grounded and is jump. For this we use pattern matching with is keyword. Then we set the jump trigger on the animator. Apart from that, we also want to handle the situation where the player goes from idle to run or from run to idle animations. We use setBool method with parameter run with the value mat.absolute player movement component data.direction greater than 0. Let's go back to Unity, recompile, press play. As you can see, jumping is working correctly. But what if I delete an player entity in runtime? Let's check. Go to player movement system and add the destruction of player entity when jumping. I think it is the simplest way in our code. Recompile, press play, jump, and you can see that we get errors. And this is due to the fact that we keep referring to a component that has not been removed from the player. What is more, the player visualization has remained on scene and we have no control over it. Okay, all that remains is to clean up this mess. Let's create player animation entity query variable and in onCreate write player animation entity query equals system API query builder with all player animation component data. This component needs to be manually removed, and with none player component data local transform, so we know that player entity was destroyed if these components are missing. Let's copy paste EntityCommandBuffer code from player visualization system. Now we just need to get the entity and player animation component data from player animation entity query. Destroy game object, that is the player visualization, and remove component player animation component data via ECB. Also add the missing require for update. Let's see if this works. Recompile. Press play. Jump to destroy entity, and voila! Everything works as expected. I warmly invite you to support us on the Patreon, where I share the code from the recordings and post the ECS videos beforehand. And to all the supporters, thank you. We really appreciate your support. Thank you for your time. In the next materials, we'll focus on the camera operation and the user interface, so stay tuned. Hello TaleForges! In today's tutorial we'll learn how to implement the camera so that it can follow player transform from within the ECS code. So let's dive in and see how it's done. First, let's add the Cinemachine package, as I want to use the camera to follow the player. Let's go to Window, Package Manager, and search for Cinemachine. Download the package. Here is an editor error which you can ignore. So let's create a virtual camera. Right-click in Hierarchy, Cinemachine, Virtual Camera. Let's reset transform and change body to framing transposer so we get smooth 2D camera movement, and reset X, Y, Z damping. Set camera distance to say 30. Set aim to do nothing. Also select tag main camera for virtual camera. Remove this tag from main camera object. As you can see, the Cinemachine brain component responsible for managing the main camera has appeared. We'll leave it unchanged. So time for coding. Okay, let's remove the destroy entity from player movement system. We don't need it anymore. Let's create a new partial class, player camera system, that inherits from SystemBase, as we will be performing manage operations, and of course implement the onCreate, onUpdate, and onDestroy methods. Then add attribute, update in group, type of simulation system group. Before we get any further, to improve readability, let's refactor the name player animation component data to player manage component data. It's much clearer. Also, let's add a game object and transform to the component and pass them at the time of creation, i.e. in the player visualization system. We can remove the ECB here along with the method and use state.entityManager.addComponentObject. Let's correct the naming. Now we can delete the game object directly in the player animation cleanup system. Alright, let's go back to the player camera system class. First of all, let's add player entity query, from which we'll get the player manage component data component. Let's not forget to add require for update. In the onUpdate method, we want to set the follow of our virtual camera, so we will use the main camera tag. So let's create virtual camera variable and then write if virtual camera is not null, return. Now we need to find camera object, so virtual camera equals GameObject.findGameObject with tag main camera, .getComponent Cinemachine virtual camera. Although this is not a very efficient method, it's enough if we only need to do it once. Next, we'll retrieve the player managed component data from entity query. And at the very end, all we need to do is set virtual camera.follow to player managed component data.transform. Let's go back to Unity and test this feature. Wait for the recompile process to finish. Press play. And, as you can see, virtual camera is correctly following the player. Hello TaleForgers, in this video we'll be implementing dead zones based on player collisions. So without further ado, let's dive in and see how it's done. First of all, let's create a materials folder. Inside, create new material and name it dead zone. Let's select surface type transparent and disable receive shadows. Now all you need to do is to change the color to red and set the alpha channel to about half the range, so that the dead zones do not cover the game background. Next, let's create a 3D object, a quad, name it dead zone, reset transform, and of course remove the mesh collider. Let's drag and drop dead zone material to mesh renderer, add the physics shape and physics body components. Let's set the physics body to static. Now configure the physics shape, set Z size to 1 and let's add new tag dead zone to physics category names. Change the collision filter belongs to dead zone, collides with player. After all necessary operations, let's create a prefab from this game object. In addition, let's add dead zone as a collides with parameter for the player prefab. We can then arrange the dead zones on the scene. Let's create a new dead zones empty game object and place two zones in it. Let's set the scale to 50, 40, 1, so non-uniform scale, which will be baked to the component data. And let's set the position manually. I will do it in fast forward. You can pause the video and move the boxes around as you like. Okay, so what's my idea for implementing this? We have a whole system responsible for checking if a player collides with the ground. I think it would be useful to use this system and extend it to check if we collide with dead zones. If so, we'll display a debug log. First, we need to open player ground component data and add two collision filters to filter the collision check for the ground and dead zone layers. Next, in player ground offering, let's add 4 new serialized fields, 2 for the dead zone collision parameters belongs to and collides with, and the other 2 for the ground. I'm using physics category tags for the fields, so I will be able to easily change the parameters in the editor, without having to beat shift. Let's create 2 getters for dead zone and ground. Create new collision filters and within them we refer to the related belongs to and collides with, and call value after the dot operator, because the collision filter parameters takes an unsigned int values, not the physics category tags. The return time is of course collision filter. At the very end of the class, we'll pass parameters to player ground component data. In the player ground aspect, let's add read-only getters to retrieve collision filter values from component data and use them in the system. Let's add a new field, private collision filter, dead zone collision filter, and pass it and ground collision filter in onStartRunning. In player ground job, let's add two parameters for collision filter and pass them in onUpdate when creating the job. Before we go any further, we need to add a new flag to PlayerComponentData, which will determine whether the player is dead. So next, in player aspect, let's add an isDead property that references PlayerComponentData. Also replace the read-only access with a read-write access. So let's back to player ground system. Let's create a new overlap box method with the BaseCompile attribute that returns a true-false value and takes the following parameters: player transform, box geometry, ref native list distance hits, and collision filter. Then let's write return collision word.overlapBox pass player transfer.position plus overlap detection offset new quaternion 0001 box geometry.size divided by 2 ref hits collision filter. We will be executing this method twice, once for the dead zone check and once for the ground. Let's remove the isGrounded check for now and write bool isDead equals overlap box player transform box geometry ref hits dead zone collision filter. Player aspect dot isDead equals isDead. If isDead, then debug.log dead to the console, and of course don't forget hits.dispose. Return. We need to implement similar code for the isGrounded check, except that we will pass the ground collision filter. Additionally, let's add an if isGrounded check and display a message in the console. Okay, that's it for coding. Let's go back to Unity, wait for the compilation to finish, and go to Systems on the ECS scene. Select player ground and set all the necessary parameters. Attention! These collision filters are set from the perspective of the player making collisions with dead zone and ground. So for dead zone belongs to player collides with dead zone. For ground belongs to player collides with ground. Alright, all set, so let's hit play and jump to the dead zone. Voila, we got a debug.log in the console. Great job! Hello TaleForges! In today's video we will focus on the implementation of a simple UI in ECS that informs us when a player dies. So let's start by creating a canvas. Right-click in the hierarchy, UI, Canvas. Next, let's set the size to vertical Full HD, which is the standard for mobile devices. It is 9:16 aspect ratio. You can also create the game in 60:9 aspect ratio, which equals to horizontal Full HD if you want. Okay, we need a window, so let's create an empty game over window object. Of course, let's set the anchor preset to stretch with press Shift plus Alt, so that the window preserves the aspect ratio for different devices. Inside it, we'll create a stretched container that we will enable at the game over. Also add offsets left and right 100, top 600 and bottom 800. so that we position the UI in the center, at a distance from the edge of the screen. Now let's create a background image in which we also set the anchor preset to stretch. Select source image to background UI. Of course, texture type is Sprite. Next, let's add a description which will be set via GameOverController based on the localization. The font can be set to size 72. Let's set top stretch for this element. Also set left position to 100, right position to 100, Y position to minus 170, high equals 400, set both alignments to center. Last thing, let's create a back to menu button that will allow us to switch between scenes. This will be covered in the upcoming materials, where we will learn how to switch between the menu and game scenes. First, select source image to button 2, then set position and pivot to bottom. Position Y equals minus 75, width and height 400. Let's set the font size to 46. Also change color to white. Let's set top position to 10. No need to remove the container. We will just disable it in the code, so you will still be able to preview UI in the Unity editor. In this tutorial, I also want to show you how to localize text. So let's go to the package manager and install the localization package provided by Unity. Select Window, then Asset Management, Localization Tables. We need to add new localization settings. Let's save in the settings folder. We haven't created any tables, so let's add a new one. We have received a warning that we don't have locales selected, therefore let's click on Local Generator and select the languages we are interested in. For me, this will be English and Polish, as I am from Poland. I saved the generate data in the settings folder. Now it is time to create a new table. This will be a table of type string, which I will call UI text. I'm going to save it in the settings as well. Now I can add two entries, one with the win game key and the other with the lose game key. I use the snake case here because the localization package reminds me of database. I type into the win game field, you have won, congratulations, which in Polish means wygrałeś, gratulacje. In the lose game field, on the other hand, I will write you lost, would you like to try again? I see tab is not changing fields in this window, which means in Polish, przegrałeś, czy chcesz spróbować ponownie? Okay, time to start coding. First of all, let's create new ECS system, Game Over System. Of course, add partial keyword and inherit from SystemBase. Let's add the update in group type of simulation system group attribute at the beginning of the class. In this class, we want to create an event which will be invoked when the player flag is dead is set to true. So let's write public event action bool game over. Now it's time to create protected override void on create and add require for update player component data, so we can check player flag in onUpdate. Next, create onUpdate method where we get singleton player entity and player component data via System API. If player component data is not dead, return. After checking the condition, let's invoke the GameOver event with the true flag and destroy the player entity. That's it. We have simple event communication. It's time to create mono-behavior controller called GameOverController. First of all, let's add the TaleForge.ui namespace and add 4 serialized fields: GameObjectContainer and TextMeshPro text, which I group like references, and 2 localized strings, WinGameTextLocalization and LoseGameTextLocalization, which I group like localized text. Let's create private void awake method where we cache GameOverSystem from word.defaultGameObjectInjection.word.getExistingSystem_manage GameOverSystem. Of course, we need to add a new private GameOverSystem variable, GameOverSystem. Then let's set container active state to false, because we want to hide it after the game starts. In the onEnable, let's add subscription to the GameOver event. In the onDisable, just unsubscribe. Let's create a private void onGameOver event bool_is_player_def method where we can enable the container and set the text depending on the player state, win or lose game text. This is how we handle our UI communication. Last thing, we don't want to change the player's input after game over, so let's extend the input system class. Let's create a private GameOverSystem class variable, GameOverSystem. Let's add a protected override void onStartRunning, which doesn't require an ISystem start-stop implementation for SystemBase. Then let's assign entity manager .word.getExistingSystemManage GameOverSystem to GameOverSystem and bind to the event via GameOverSystem.GameOver plus equal onGameOverEvent. Now let's create a private void onGameEvent bool_state method in which we disable input controls. Don't forget to unsubscribe event. Alright, let's go back to Unity, wait for compilation process to finish, add new component GameOverController to GameOverWindow, and set the serialized fields, so container, text, and localized text, win game, and lose game. I forgot to add localized text for back to menu, so let's go to the localization tables and create new field, back to menu. Of course, add English and Polish localizations. Then let's go to back to menu text in Unity hierarchy and add new component, localize string event. Select string reference to back to menu, then add new update string event, pass back to menu text reference and select text. Okay, let's see if everything is working. Press play and go right to dead zone. The UI appeared, a message was received and the player was destroyed. In addition, hitting the input keys doesn't generate any errors, so we have effectively protected ourselves from undefined behavior. Well done! Hello TaleForgers! In today's material we'll focus on the implementation of triggers in ECS. Our goal is to reach a certain point, detect the player and activate the UI where we can move on to the next level. So let's dive in and see how to implement this. Firstly, we want to separate the logic of the menu from that of the game. So we assume that we will create a second scene, menu, which will be the start scene and from which we'll launch the game scene. Of course, this scene can be freely modified, for example by adding options, credits, etc. But we'll focus on just starting and quitting the game. In today's video, we'll focus on the part where the player is detected by the trigger at the end of the level. In the next video, we'll implement switching between main and game scenes and ECS subscenes. So let's create a new sprite object, which we name EndFlag. As always, texture is set to Sprite2D and UI. Set sprite to EndFlag. Then add new component, physics shape. Set collision response to race trigger events. In the collision filter settings, let's add a new physics category name, EndFlag. Then select EndFlag for belongs to and player for collides with. Of course, let's make a prefab from the EndFlag object. Also, let's clean up a bit here, create two folders, bullets and player, to group prefabs. Set uniform scale to 4. Next, duplicate ground and position it in the scene. Also, position EndFlag to match the position of the ground. Now it's time to create a next level window in the UI canvas. Let's duplicate game over window and rename it to next level window. Set left and right position to 200, top 700, bottom 900. Also, let's change the color of the background to more orange. Rename objects to next level button and next level text. Next, change anchor of next level button to center. Adjust position and change width to 450. OK, go to localization tables and add new record, next level, for English and Polish localizations. Now let's back to next level button, select text and change string reference to next level. This is it for the Unity editor configurations. Let's get to coding. I'm committed to stateless collisions, and while we could use the stateful triggers discussed in the official Unity examples, linked in the description to the video, for this task, we're going to approach the problem in fundamentally different way. We can refactor the player ground system class to player detection system, which will be responsible for detecting when the player collides or triggers entities in the game world, and for setting flags when an entity is detected. Of course, changes also apply to related scripts. So let's start by refactoring the name from player ground component data to player detection component data. Then add new field, EndFlag collision filter. Next, let's refactor the name for player ground affering and player ground breaker to player detection affering and player detection breaker, respectively. Let's add EndFlag belongs to and EndFlag collide with serialized fields. We need them to pass collision filter settings all the way to player detection system. Also create getter with collision filter return type, of course with EndFlag parameters. Don't forget to pass EndFlag collision filter in the breaker. Now go to the player ground aspect and refactor the name to player detection aspect. Also remember to change player ground component data name. Then add new getter, EndFlag collision filter. Finally, let's rename player ground system and player ground job to player detection system and player detection job, respectively. So from the beginning, Let's create a private collision filter and flag collision filter field. In onStartRunning method, let's assign this field to player detection aspect and flag collision filter. Then we can create checkbox method. It is faster approach than overlap box, and we don't need hits in case of ground and dead conditions. Fix cause and remove debug code. Also remove hits.dispose from isDead and isGrounded condition checks. Then let's move the hits code down. Let's add two fields to job, public collision filter and flag collision filter, and EntityCommandBuffer ECB. Don't forget to pass ECB and collision filter to job. Let's copy getEntityCommandBuffer method from player movement system and paste it in the player detection system. Of course, add missing require for update and pass parameters to job. I want to save invocations of the job when there is no need, so let's get singleton player component data and check if player is dead. If so, return. Also check if next level component data exists. If so, also return. This will be helpful as we add next level component data, so we can return early if this component exists. Again, add missing require for update. Let's go back to job implementation. Let's write bool is and flag equals overlap box, player transform, box geometry, ref hits, and flag collision filter. In this case, I want to get hits because I can add next level component data to the hits at 0 index entity. Why do this? It will allow me to check via level system, which I will create later in this video, if any next level component data exists, and if so, invoke the next level event. So if is end flag ECB.addComponent hits at 0 index dot entity new next level component data, and at the end add hits.dispose. So it is time to create the next level component data struct. Before we move on, I warmly invite you to support us on Patreon. Any support is really appreciated and important. On Patreon, I share materials in advance and add various useful code snippets. So back to the code, create a new file next level component data that implements IComponentData. Add public bool is invoke. Setting this flag allows us to invoke the event only once. Then let's create level system class, which will be SystemBase. We'll use manage_action class to communicate with UI. Implement missing functions. Add update in group type of simulation system group attribute and new public event action next level. Prepare onCreate method in which we add require for update next level component data, so system will not update if next level component data doesn't exist. Inside onUpdate method, let's write var next level entity equals system API dot get singleton entity next level component data. Also get singleton next level component data because we need to change the isInvoke flag to true. If next level component data is invoked, return. Let's invoke the next level event and then set next level component data is invoked to true. Set next level component data via entity manager. pass entity and modified component data. Last time we created GameOverController, but I want to improve the naming, so let's rename this class to GameOverWindowController. From now on, we'll mark all classes that relate to the UI and are windows with the word window in the classes. This will improve the readability of the code. Also, let's add UI directory to group UI classes. Now it's time to create next level window controller so we can handle UI logic. Let's create new file in the UI folder, next level window controller, which inherits from mono behavior. Create serialized field, GameObjectContainer. Also add header, references, attribute. Next, create private level system field. Then in the awake method, let's assign level system to word.defaultGameObjectInjectionWord .getExistingSystemManageLevelSystem. Let's also disable the container at startup. In the onEnable method, let's add a listener for the next level event. In the onDisable, remove listener from event. Finally, let's create a new method on next level event, in which we will activate the container. That's it for the code. Let's go back to Unity. Wait for recompile process to finish. Let's refactor player ground to player detection and set up endFlag collision filter belongs to and collides with. Also attach next level window controller script to next level window. Remember to remove GameOverWindowController script from newly created object. Press play and test if everything works. UI has opened, so yeah. One last thing, let's add an input log while the window is open. So let's move to input system and create new field, private level system. In the onStartRunning method, assign level system to entityManager.word.getExistingSystemManageLevelSystem and subscribe to the next level event. In the onStartRunning method, let's remove listener to the event. Finally, let's create an onNextLevelEvent method that simply disables input controls. Let's go back to Unity, recompile, clear console, and press play. Now use input, and we are not moving. Great! Hello TaleForges! Today we will implement the logic of the following UI classes. Next level window controller, from which we go to the next level, so ECS subscene, GameOverWindowController, from which we will return to the main scene, ManyController, from which we go to the game scene, and of course ECS systems like level system and extend GameOverSystem and input system implementations. We will cover loading screen trigger when switching between subscenes or scenes in our next video. So let's dive in and see how it works. First, let's fix the behavior of some buttons. Look at button 2 in the project. As you can see, these buttons have a lot of empty space, which is not good for input because we can click on this empty space. It is writecast. So solution for this is to have cropped image to the desired size. So I can replace buttons with new ones, and now it is necessary to adjust the back to menu and next level buttons. For back to menu button, let's set width to 400, height to 125, position Y to 50. For next level button, let's set width to 450, height to 125, position Y to -45. That's it! Let's start coding. And let's start from refactoring player animation cleanup system to player manage cleanup system. Also variable to player manage entity query. Level references, i.e. subscene references, can be stored in the list of entity scene references. However, I want to access them via the game scene, not via each level scene. So I decided to use the singleton pattern. I'm not a big fan of this pattern, but in this particular case, where I want to get access to subscene data from level system, it really makes sense. So let's create a new class which inherits from mono behavior. And add serialized field, private, list, entity scene reference, entity scene references. Of course, also create getter. Let's prepare public static level references instance with public getter and private set. Then, in the awake, if instance is not null and instance not equal this instance, then destroy game object and return. Otherwise, let's assign instance to this and mark the instance as don't destroy on load, so pass this or instance as parameter. That's it! We have created our singleton class, which is like a model for data. Okay, we are in the level system class, so what's the plan? First, we're going to create two events, last level complete and level loaded. We need this to communicate with other systems, for example, input system. Also, when I call load scene, I have to cache the entity current scene because I need it to unload the scene later in the game. What's more, I will increase the current level index variable when subscene is loaded and reset when game scene is loaded. It's time to implement load next level if current level index is greater than level references.instance.entityscenereferences.count -1, then invoke last level complete event and return. Otherwise, unload previous level and load next subscene. So let's create unload previous level method. If entity.null.equals current scene, return. Otherwise, debug.log unload subscene just to inform us in the console. Then let's write scene system.unload scene, word.defaultGameObject injection word.unmanage, and pass current scene. Now let's create load next subscene and write debug.log load subscene. Then current scene equals to scene system.load scene async, pass word.defaultGameObject injection word.unmanage, and as the second parameter, level references.instance entity scene references current level index ++. At the end, call level loaded.invoke. Then, in the onCreate, let's subscribe to scene loaded. We need to reset state when game scene is loaded. Don't forget to remove subscriber in the onDestroy. Let's implement onSceneLoaded method with two parameters, scene and load scene mode. Inside it, let's write if scene.buildIndex not equal to int scene type game, return. Otherwise, set current level index to 0, current scene to entity null, and load next level. I want to add scene type enum to avoid magical string variables in the code. So let's create a new scene type enum in which we are going to add many endgame elements. This approach is resistant to the scene name changes, however is vulnerable to changing the order in the build settings. Also adjust namespace to TaleForge.core. Okay, then let's move to implementing UI logic on the game scene. We need to load next level after level completion and return to main scene if the game is over. In the next level window controller, let's add a new serialized field, private button, next level button. In the onEnable method, let's add a listener to on next level button clicked, which I will create in a moment. Also remove the listener in the onDisable method. Now create new method, on next level button clicked. Here we can use load next level via level system. Don't forget to disable the container after the button is clicked. Okay, so we have logic for next level window. It's time to adjust game over window controller. In this class, we also need to add a serialized field for button. Then let's create a level system variable because we have to unload previous level, subscene, before we move to the main scene. It is a very important step due to the fact that we want to make sure that everything related to ECS is properly disposed of. Next, add listener to on game over button clicked in the onEnable, and remove listener in the onDisable. Let's create the on game over button clicked method where we can unload previous level thanks to our implementation of the level system. Oh, let's fix private to public. And then load the main scene via the Unity Scene Manager. At the end of the method, we disable the container. Last time we handled situation when player lose game, but what about win? Let's go to game over system and add a new variable, level system. And then a new onStartRunning method. Assign level system to word.defaultGameObjectInjectionWord.getExistingSystemManageLevelSystem, and then subscribe to the last level complete event. Remember to unsubscribe in the onStopRunning. Next, create a void winGame method. Here we want to call the game over event, but with a false flag because the player didn't die, so he won the game. Also add the code necessary to destroy the player entity so that the player managed cleanup system can do its job. Okay, what's next? During testing, when recording video, I found a rather nasty bug. After reloading a scene, the camera didn't reset. Why did this happen? Because I never set virtual camera to null. So what is the solution? I need to check if virtual camera.follow is null. If so, assign transform to follow. So let's refactor player camera system. Let's change if sign to equals and paste virtual camera assignment code. Then write if virtual camera.follow not equal null, return. Also add debug.log, player visualization, player entity query, get singleton entity.index, because I want to check if, when changing subscenes, the player index changes. If so, everything works as expected, because we have new player instance on the new subscene. Another important thing is to re-enable input controls after a level change. We can delete inputControls.enable in the onCreate method because we are going to enable input only in-game. Let's subscribe to level loaded event in the onStartRunning method, create new onLevelLoaded method and write inputControls.enable. Also unsubscribe in the onStopRunning. I invite you to support us on Patreon. Any support is really appreciated. On Patreon I share materials in advance and add useful code snippets. Okay, last thing to do in the code, let's create the menu controller script. First, add two serialized field buttons, one for start game and the other for quit game. Also add a header, references. When menu is enabled, let's add listeners for the corresponding events. Of course, don't forget to remove listeners in the onDisable. Also create onStartGameButtonClick method where we load game scene. Let's use the scene type enum here. Let's create an onQuitGameButtonClick method where we call applicationQuit. Okay, let's go back to Unity, select event system on the scene and replace with new input system. Remove debugDisplay.drawComponent, then pass necessary references to the next level window and game over window. Let's open ECS game scene and make prefab from the level object. Rename prefab to level 1. Duplicate this prefab and rename it to the level 2. Also, let's make prefab from systems object. Then create levels directory and move level prefabs to it. Okay, it's time to rename our level scene to ECS level 1. Duplicate this scene. Then rename the second scene to ECS level 2. Open scene and change level 1 prefab to level 2. Let's also change one of the ground position so we can see immediately if the scene changes. Change the background to the other one. Okay, back to game scene. Let's remove ECS game scene from hierarchy and create level references object. Add component level references and select references to ECS subscenes. Finally, let's create a new menu scene, remove directional light, and let's create a canvas. Set canvas render mode to screen space overlay, then UI scale mode to scale with screen size. Let's set reference resolution to Full HD. Match to width. In the canvas, let's create menu object, set anchor to stretch. Then create content object, also stretched. Inside it, let's add background. Just left it white. And create two buttons, Start Game button and Quit Game button. Of course, let's add menu controller script and pass references to buttons. Then position objects, select source image, adjust size and fonts. I will do it in the fast forward. Last thing to do, let's add scenes to build settings. Great, we are ready to test. Okay, let's go to the end flag. We get next level window. Click on the button. Great, second level is loaded. Time to win game. Let's go to the end flag again. Go to the next level. But we don't have more levels, so this time we got game over window. Fantastic! Let's back to menu. Everything works as expected. After restart, also game is working. However, after implementing this solution and testing in the Android build, entity scene reference returns null. According to the documentation, the build process only detects offering scenes referenced by entity scene reference, so bake references, and subscene mono behaviors. The build process doesn't detect scenes references by GUIDs, and their entity scene files will be missing from builds. For this reason, you should avoid using GUIDs to identify scenes and also avoid using entity scene references, which is not directly said, in the serialized field references. My idea is that we will add a new scene main, which will always be loaded, and will have scene loader subscene, so that when we fill the buffer with levels in Baker, we can easily get entity scene references of the levels. First of all, let's create a new directory named Dynamics Buffers. Inside it, let's create an entity scene reference buffer element data struct, which implements iBuffer element data. Each element of the buffer needs to store reference to subscene, so let's add a new public entity scene reference field. Now let's create a new script, entity scene reference offering. We'll base it on the documentation example. Let's add if Unity editor and end if. Then create serialized field, private list Unity editor.sceneAssets levels. Of course, let's add getter for this variable. Next, let's prepare entity scene references baker class with bake method. Inside this method, we want to get entity, so we can add buffer with entity scene reference buffer element data type. Then let's write for each var scene asset in offering levels buffer.add new entity scene reference buffer element data entity scene reference equal to new entity scene reference scene asset. We can remove level references script, we don't need it anymore. Also, let's remove it from the game scene. So now we can easily get the entity scene references to levels via system API.getSingletonBuffer in the level system. Let's modify the logic to handle additional main scene. Refactor entity current scene to current entity scene. Create a new private scene type current scene variable in which we will store the scene to unload. Then let's create a new load scene method with two parameters, scene type and load scene mode. Inside it, let's add the debug.log load scene type and check if current scene is not equal to scene type.main, because we want to unload the previous scene, like menu or game, only if it is not main. So in other words, we want to have main scene always available. Of course, add it to the scene type and change order. So main is first scene, menu second, and game third. Let's write scene manager.unload scene async int current scene. Next, scene manager.load scene async int scene type scene mode, and assign scene type to the current scene variable. We also need to modify load next level and load next subscene methods. So var entity scene references dynamic buffer equals to system API.get singleton buffer of the entity scene reference buffer element data type. Then change reference of the level references.instance to the dynamic buffer.length. Same changes applies to the second method, load next subscene. So let's copy paste getter. However, in this case, you want to get element of the buffer at the current level index ++ and also refer to the entity scene reference. Okay, let's add load scene many with additive mode in the onCreate method. From now on, we'll start from main scene. Okay, let's refactor some code so we will have calls to the scene manager in the one place, level system. Create level system variable and add awake method in which we will get level system. Then, in the onStartGame button clicked, let's remove code and add level system.loadScene game with additive mode. Then polish call in the game over window controller load scene menu, also with additive mode. So let's go back to Unity, wait for compilation process to finish, and create new scene, main. In this scene, let's create a subscene, scene loader. Inside this subscene, add the entity scene references object and attach entity scene references offering component. Remember to pass level references to the list. Also add main scene to build settings and fix order. Okay, so let's test if the scene loading process is still working correctly. As you can see, it works in the editor, but now also in the build. Hello TaleForges. In this video we'll focus on the loading screen implementation, which will complete the scene management part. We'll learn interesting mechanisms for async code execution, especially waiting for the ECS subscene to load, so let's dive in and see how to implement this. First of all, I want to install Unitask, which provides efficient allocation async await integration for Unity, and thanks to Unitask, we can await on the async operation, which is really great, so I added a link to the package in the video description. So let's scroll down and select Getting Start section, click on the UPM package and copy Git reference. Okay, go back to Unity and select Window, Package Manager. Then click on the plus icon and select Add Package from Git URL. Paste the copied link and press Add button. Now we need to wait for compilation process to finish. Let's start by extending the level system logic. First, we'll add a new public const int animation time in milliseconds parameter and set it to 1000. We'll need it to wait for async operations as well as animations on the loading screen scene. So let's add new private async Unitask method, loading screen, which will have one parameter. Bool is enabled. If this parameter is set to true, we need to await on the load scene async loading screen. We'll add loading screen to the scene type later in the video. Of course, load scene mode additive. Also important note, we can wait for the async operation thanks to the Unitask package. Without this package, we have to write some code to handle await. Then we want to wait for animation to finish, so let's call await unitask.delay, animation time in milliseconds, and the last thing in this method, if isEnable is equal to false, then we unload the loading screen scene. Next, let's change void load scene to async void load scene, because we want to wait for the loading screen as well as other load or unload operations, and add await loading screen true, so we start loading screen process. Also, let's add await to the unload scene async and load sync async. Finally, call await loading screen false, so we disable loading screen panel. In the load next level method, let's add async keyword and a new parameter. Bool is loading screen with the default value set to true. Now write if is loading screen, await loading screen, true. Add await to the unload previous level and load next subscene, which we will change in a moment. At the end, call await loading screen false. Okay, it is time to modify unload previous level, so let's change code signature to async unitask. We need to wait for the ECS subscene to be unloaded, so I found in the documentation one useful for us method in the scene system, isSceneLoaded. So I can write while scene system isSceneLoaded word.defaultGameObjectInjectionWord.unmanaged current entity scene. Await unitask yield. This is similar to calling yield return null or yield return new wait for end of frame in the coroutines. Great, so we have ECS code to wait for the subscene to unload. Next, let's change the load next subscene from void to the async unitask. I can copy and paste the code from unload. The only difference is the sign, because in the load case we need to use negation. And that's it. Last thing to do, let's add false to the load next level method in the onSceneLoaded. Okay, it is time to modify scene type because we need to add loading screen type. Before we move on, I would like to invite you to support us on the Patreon. Even a small contribution will help to develop the channel and the quality of the content present. Link in the description. Okay, let's back to the code and create new script, loading screen animation controller. It is monoBehavior class, which will be responsible for simple fade animation on the UI. So let's add two serialized fields, image and text. Of course, add necessary usings. Also create private level system variable because we need to react on the level loaded, subscene loaded or scene loaded events. Level system is equal to the word.defaultGameObjectInjectionWord.getExistingSystemManageLevelSystem. Then subscribe to the level system.levelLoaded event to the onLevelLoaded method. Also, let's subscribe to the scene manager.sceneLoaded to the onSceneLoaded method. I want to use the crossfade alpha, which based on the canvas renderer alpha, so let's set alpha to 0 in the onEnable, both for text and image. Then let's call fade method with parameter 1. Of course, don't forget to add onDisable and unsubscribe from events. Okay, it's time to create private void onSceneLoaded scene load scene mode method. If scene.buildIndex equals to the loading screen, then we can early return. But otherwise, we want to set fade to 0 because the other scene is loaded and ready to play. Next, let's create private void onLevelLoaded, so when subscene loads, we want to fade to 0. And finally, let's implement fade method. It is private void function with float fade value parameter. Inside it, let's write text.crossFade alpha fade value level system.animation time in milliseconds divided by 1000 false. The first parameter is responsible for setting the alpha, seconds is the duration, and the last one is a parameter that ignores the time scale. That's why I pass false. I don't want to ignore time scale. Let's write same code for the image. Let's go to the Unity editor, wait for the compilation to finish, then copy and paste the main scene. Rename it to loading screen and open the scene. Inside it, let's delete everything except canvas. In the content, let's add 3 things: background, image, and text. Of course, set everything as you like. I will leave some simple message and will fast forward this process. The most important part for us is to correctly add new loading screen animation controller and drag references to text and image, because we want to animate it during loading, even if it is simple fade. Now, let's open build settings and add our newly created scene, loading screen. Last thing to do, let's change sort order to 1000, because we want to overlay everything with the loading screen. Okay, let's test the behavior. I suggest we test the full game loop so we can see how it works. Also, watch the scenes that load and unload in the hierarchy tab. As you can see, everything is working correctly and we have implemented simple loading screen. Hello TaleForges, I thought long and hard about what to focus on in this material and decided to discuss the little known and little understand topic of BlobAssets. The first sentence from the documentation is extremely important. BlobAssets represent immutable binary data, because all the benefit of using BlobAssets and their performance comes from the fact that the data is read-only binary. In this sense, they are a great addition when passing data, because we can rewrite data from ScriptableObject to BlobAsset. But that's not all. If we have high-order filter coefficient, or a machine learning training set or any other large data set, BlobAssets come to the rescue. Going forward, the data they contain must be value types. In addition to the standard value types, 3 special data types are supported: blob array, blob pointer, and blob string. Okay, enough theory. In the description I put a link to the documentation and encourage you to read it. And let's focus on the implementation of the working example. Let's start with the basics. We need a container to store Collectibles data. In our case, it will be float points. So let's add a directory, BlobAssets, and inside it create struct collectible container with public float points variable. Next, let's create a struct collectible pool, which in turn will store a blob array of collectible containers. Since collectible container is a struct and has value types, we can pass it as a dynamic type to the blob array, and it will be understood by the compiler. So let's go one step further. We need to access our data from within the ECS, right? That's why we need to prepare Collectible-Component-Data struct. Inside it, create a BlobAsset reference with the type of the previously created collectible pool. Finally, we can create the Collectible class, which obviously is mono behavior. We need to pass data from the scene, and in the future from ScriptableObject, but for the sake of the example, we simplify. Let it be a list of points for collectible collected by the player. So now let's create a baker, and inside the bake method let's get an entity with the non-transfer flag. Write var collectible BlobAsset equal to create collectible BlobAsset offering.collectibleData. Then let's start implementing the method private BlobAsset reference collectible pool, create collectible BlobAsset read-only list float collectible data. I can use read-only list because I don't need to modify any elements of the list within the method. And inside this method, the BlobAsset magic will begin, which is not at all as scary as it might seem, so let's go one step at a time. First of all, let's write using var builder equal new blob builder allocator.temp. Here, let's stop for a moment. First of all, by using keyword, we are guaranteed that after the completed operation, it is, in our case, return, blob builder will be disposed. Secondly, blob builder serves us only to create BlobAsset reference and later we will not need it. That's why we are going to use allocator.temp. Next, let's create ref var collectible pool equal ref builder.construct root collectible pool. As you can see, I use ref keyword, any blob array, pool, blob string, etc. must be referred via reference, not value type. So let's allocate memory for blob array. Create blob array builder variable and pass parameters. The first will be collectible pool.collectibledata, that is our array, and the second will be the size of that array. Next, we want to fill the array with data. It is rewrite the list into the blob array. We use for and create new components in a loop, passing the points to the container variable. Finally, we can create a BlobAsset reference for collectible pool from the builder, where allocator is set to persistent because we don't want the data to be released from memory while the application is running. So now let's register the BlobAsset to the baker via add_BlobAsset ref collectible BlobAsset out _. We don't need to use hash, that's why I use discard variable. According to the documentation, if you don't register a BlobAsset to the baker, the ref counting doesn't update and the BlobAsset could be deallocated unexpectedly. Don't forget to add our CleanupComponentData with collectible blob array reference. The last thing to do, let's create a collectible system, which in this video we will use to test the operation of BlobAsset, so we get a minimal working example. Let's implement ISystem and ISystem start stop, and of course create missing members. Add the base compile attribute for each method and at the top of the class. Also add update in group attribute, type of simulation system group. In the onCreate, let's just add require for update collectible component data. We want to test whether our system is running. For this, we'll use the onStartRunning method. Inside it, let's write var collectiblecomponentData equal systemapi.getSingleton collectiblecomponentData. Ref var collectiblePool equal ref collectiblecomponentData.collectiblePoolReference.value. Ref blob array collectibleContainer collectibleData equal ref collectiblePool.collectibleData. As you can see, I use ref everywhere according to the guidelines in the documentation, just to make sure that I always refer to the right place in the memory. What remains for us is to create a for loop and display the elements of the array in the console. Let's wait for the compilation process to finish, clear console from some editor errors, and go to the Systems prefab and create empty object, name it Collectibles, then attach collectible buffering component. So now let's add some numbers to the list so we have a way to test the result of the implementation. I think 6 numbers will be enough. Okay, let's run the game and see if we got the same numbers as we entered in the prefab. Let's have a look at the console. Yes, we got the correct results. We managed to correctly implement a minimal working example for BlobAsset. Good job! Hello TaleForgers! In this video we'll expand the BlobAssets topic to include retrieving data from ScriptableObjects. We'll be able to collect objects and show a message with points. So let's waste no time and get started. First of all, let's create a collectible type enum, which will come in handy when defining our data container, that is ScriptableObject. Let's add 3 values, none, gold coin, and bronze coin. Next, let's move on to creating an SO. Let's create a new directory, data, and inside it, an empty class, CollectibleSO, inheriting from the ScriptableObject. If anyone doesn't know what ScriptableObject is, in a nutshell, it's a data container that we can modify from the editor. A great design tool that allows us to tweak parameters and requires no programming skills. Okay, adjust namespace to the TaleForge.ecs. So let's add create asset menu attribute with file name new collectible, menu name TaleForge/collectibles. We need 2 parameters, the collectible type created earlier, and the points, which in turn we used in the previous video. So let's go to the Unity and add a new directory called data. Here we can add 2 scriptable objects, one for bronze coin and one for gold coin. Of course, set the corresponding collectible types. For the gold coin, I set 5 points, and for the bronze coin, 1 point. Now it is time to go back to the code and add collectible type in the collectible container struct. Okay, so let's adjust the implementation of the classes collectible buffering and baker. First of all, let's modify the float parameter to the collectible SO for both serialized field and getter. In the create collectible BlobAsset method, let's replace the float type with collectible SO. Then let's cache the collectible data index. We will need the data to retrieve 2 variables, type and points. And remember to pass the parameters to the array builder. It's time to handle collectible detection. So let's go to the player detection component data and create a new field. Public collision filter, collectible collision filter. Then, analogous to what we did in the previous videos, we add collectible belongs to and collectible collide with a getter of type collision filter. In bake method, let's pass collectible collision filter as a parameter. Next, go to the player detection aspect and add new getter, public collision filter, collectible collision filter, player detection component data .value ro .collectible collision filter. It is time to extend the player detection system implementation. First, let's add the private collision filter, collectible collision filter field. Of course, we need to assign the variable in the onStartRunning method. we get the value from aspect. Next, let's pass the collectible collision filter to the player detection job, in which we need to define another variable. First, let's refactor the previous code, move the check to see if the player is grounded to the handleGround collision detection method. Next, let's wrap the code responsible for checking whether the player has reached the end flag in the handleEndFlag collision detection method. Now we can create a new method, handleCollectible collision detection, and pass two parameters, local transform and box geometry. Let's add burst compile attributes to each of the newly created methods. Now create a native list to store all the detected hits, of course with the allocator set to temp job. And let's do a check. Bool is collectible equal overlap box local transform, which let's refactor to player transform, then pass box geometry, ref hits, collectible collision filter. If a collectible hit is detected, let's go through the list of all the hits and add a component to the entity, collected collectible component data. Finally, let's remember to add dispose for the hits. We need to add flag, our marker, so let's create new IComponentData, collected collectible component data. We treat this as a flag only, without any fields. And we get rid of the error in the player detection system. We need to specify the type of objects we are placing in the scene, so that we can retrieve the necessary data at the time of the call. There are advantages and disadvantages to this approach. The advantage is that we only keep the type in memory, without all the necessary parameters. In our case, it's only one additional parameter, points, but in reality there could be a lot of them. Then each component data, and let's say there are thousands of them, would occupy memory. On the other hand, the disadvantages are the increased complexity of the code and the need to search through the BlobAsset to find the type corresponding to the collectible. Okay, so let's add a public collectible type variable. Next, let's create a scene collectible offering class inheriting from monoBehavior. By standard, we'll add a serialized field, collectible type, with a getter. In the baker, we need to get entity and add component, scene collectible component data with parameter type. Thanks to this implementation, we'll be able to determine which collectible is detected. Okay, let's select the collectible system. First of all, let's change update in group to update after. I want to execute collectible system after player detection system. I can also remove ISystem start stop interface. I don't need it anymore. Copy and paste blob array related code to the onUpdate method, and of course remove onStartRunning and onStopRunning methods. Let's create private entity query collected collectible entity query and write inside onCreate entity query equals systemapi.querybuilder.withAll collected collectible component data.build. Don't forget to add state.require for update collected collectible entity query. It's time to handle collectible logic. We'll need native array entity with temp allocator with all our collected collectibles. Then inside the for loop, we can iterate over each element and execute collectible logic. Pass parameters, ref state, collected collectibles, index, and ref collectible data. At the end of the method, dispose native array. So let's implement base compile private void execute collectible logic, ref system state state, native array, entity, collected collectibles, int index, ref blob array, collectible container, collectible data. I want to show debug.log with points and destroy collected entity. So let's get component scene collectible component data, pass collected collectible at index as a parameter. Next, let's write for loop and cache collectible data in the collectible container variable. If collectible container.type equals scene collectible component data.type, we can execute debug.log logic, destroy entity collected collectible index, and break. Great. Okay, back to Unity, wait for the compilation process to finish, and let's create a new folder inside graphics, 3D. Then add the collectible models. For me, it will be gold coin and bronze coin FBX. Let's go to the prefabs folder and add a subfolder, collectibles. We need to prepare abstract prefab and two variants prefabs for gold and bronze coin. So let's create an empty object on the scene. First of all, let's add two components, physics shape and physics body. Physics body will be static, so there is no a big problem. For physics shape, we need to configure the collision filter. First, let's add a new physics category name, collectible. Then we can set belongs to parameter to the newly created collectible and collide with setting to the player. This will allow us to detect collision with the object. Attach new component, scene collectible offering, and leave it as default. Important note, the only way children get automatically deleted when destroying the parent is if the parent has a linked entity group buffer on it. This is added by default to baked prefabs, but not game objects in a subscene. That's why we need to add linked entity group offering component. Drag and drop collectible to folder and delete it from the scene. Now we can create two prefab variants, collectible gold coin and collectible bronze coin. Inside the first one, let's drag and drop gold coin, select gold coin type, adjust Z position, and fit enable render meshes. Inside the second one, drag and drop bronze coin, select bronze coin type, also adjust Z position, and fit enable render meshes. And that's it. Let's go to the ECS level 1 scene, select Systems Prefab, open it and select Collectibles object, remove all elements from the list, then drag and drop our data, collectible gold coin and collectible bronze coin. Next, select Player Detection object and choose collectible belongs to as player and collectible collide with as collectible. Now it is time to add coins to the scene, so open the level 1 prefab and put 2 coins in it. It will do it fast forward. Okay, it's time to test everything. Go to the level scene, pick up collectible and we got an error. Let's check it out. As you can see from the error description, EntityCommandBuffer was recorded in the TaleForge ECS player detection system and played back in Unity entities and simulation command buffer system. The problem is inside the player detection system, which refers to an entity that doesn't exist. One of the solutions to this problem is to add the order last true parameter to the updateInGroup attribute. Okay, let's see if everything is working properly in the Unity and play the game. Move to the Collectibles and... yes, everything is working fine. Awesome. Hello TaleForges, in this video I want to finish the collectible part and show you how to update points on the UI using DOTween animation. I will also use model view controller pattern to implement the UI logic, so let's dive in and see how to do it. First of all, let's create a new struct pointsComponentData which obviously implements the IComponentData interface, and add a public float field points. This component will help us to communicate with the point system later. In this system we have two options. Either we get rid of the base_compile attribute and change the ISystem to SystemBase, or we leave the current logic unchanged and add the component to newly created entity, which is a kind of abstract entity as it has no visual representation but will only have a pointsComponentData component. So let's start with the refactoring. Let's cache collected collectible index to the entity variable. Of course, replace the old code with the entity variable. Also remove debug.log. Now we can write var pointsEntity equals state.entityManager.createEntity. This method will create an empty entity, so we need to add a component data, pass pointsEntity and create new pointsComponentData. Assign points using collectibleContainer.points, and that's it. We are going to sum points in the pointSystem class. So don't waste time and let's create a new class, pointSystem, which inherit from SystemBase. Implement missing members and then add update after type of collectible system attribute. We need to create public event action float points updated. This will let us to communicate with the UI and update points view. Next, let's prepare three member variables: private entity query, pointsEntity query, private level system, and private float, points. I will use them in a moment. It's time to implement onCreate method. Inside it, let's write pointsEntity query equals systemapi.queryBuilder with all pointsComponentData and of course build. Logic requires two things: resetting points and adding them. So let's start with the easier case, resetting points. Let's add onStartRunning method in which we can cache level system so we are able to subscribe to level loaded event and reset points. Also create onStopRunning method in which we can unsubscribe from level loaded event. Then let's implement new method onLevelLoaded and inside it set points to 0. Let's invoke pointsUpdate events and pass points. Great, now we want to handle onUpdate method, so let's get data from entity query, pointsEntities and pointsComponentData array, both with allocator.temp. At the end of the method, call dispose. Next, let's implement for loop in range from 0 to pointsComponentData array.length. We can cache single pointsEntity and component data. Now let's sum up the points and destroy entity. We don't need it anymore. Don't forget to call pointsUpdated.invoke points. We want the UI to be updated, right? I have decided to showcase the DOTween package a little as the package has both a free and paid version, providing a ton of useful UI animation tools. So let's go to the package manager, my assets, and download the package. If you haven't added a package yet, go to the asset store and add a DOTween. And the package will appear here. Once you have downloaded the package, you can import it and wait for the process to finish. Finally, we can set up the DOTween package, so let's select Setup and check TextMesh Pro in the modules. Confirm and let Unity propagate the changes. OK, go back to Rider. First of all, let's create 3 classes: PointsController, PointsModel, and PointsView. I want to implement a MVC pattern which allows me to split logic from view and data. Controller manipulates model, update data, and update view, presentation. View knows about model, get data, and model doesn't know about other classes. OK, so let's start with the PointsController. Inherit from monoBehavior and add required component type of PointsModel, type of PointsView attribute. So when I add the controller component via the Unity editor, it will also add PointsModel and PointsView. It's time to create variables: private PointsSystem, PointsSystem, private PointsModel, PointsModel, private PointsView, PointsView, and private float, previous points. In the awake method, let's assign PointsModel to getComponent PointsModel. The same operation for the PointsView. We are sure that this object contains these 2 classes thanks to the required component attribute. At the end of the method, let's cache PointsSystem word.defaultGameObjectInjectionWord.getExistingSystemManage PointsSystem. Now we can implement onEnable and onDisable methods, subscribe and unsubscribe to the PointsUpdated event. Of course, we need to create new method onPointsUpdated with a float parameter points. First, let's call PointsView.UpdateView and pass previous points and points. Don't forget to cache previous points, so the next time we call the event, we can animate our points on the UI from the previous value to the new value. Great, let's go to the points model. In this class we want to store data, so let's create 2 serialized fields. One for TextMesh Pro and second for the points animation time. Obviously we want to create getters so controller or view can get data. So let's implement PointsView class, which must inherit from monoBehavior and have the required component type of PointsModel attribute. Let's add private PointsModel PointsModelMember variable and cache it in the awake method via getComponent. OK, it's time to implement public void updateView method with 2 parameters: float previous points and float points. Inside this function, let's write do virtual float previous points PointsModel.pointsAnimationTime and create lambda expression value PointsModel.pointsText equals points open brackets value : f means fixed point, by default 2 decimal places. OK, go back to Unity. Wait for compilation process to finish. We need to add UI representation for the points. So let's open game scene. Inside it, select canvas and create a new object. Call it points. Let's set anchor to the top left with the X position set to 50 and the Y position to -50. Then create TextMesh Pro child. Set anchor also to the top left, write some default text and change font size to 48. Next, let's add new component, PointsController. As you can see, PointsModel and PointsView have also appeared thanks to required component attribute. So drag and drop the text reference to the PointsModel. Now we are ready to test points, so go back to the main scene and press play. Let's collect some coins. Great, we have a working UI with animation on the DOTween. Let's see if the points reset when you reach the next level. Yes, fantastic! Hello TaleForges, in this video I want to show you platform's movement with some nice additions, namely Gizmos and handles. So let's dive in and see how to implement this. As you can see, I created 3 files for myself beforehand: platform movement component data, platform movement authoring, and platform movement system. I also prepared a simple base to extend, so you can pause and rewrite as you follow along. We are going to approach the problem as follows. We are going to add our platform movement component data to the entity we want to move, which will allow us from within the system to run a query, go through all the entities of interest in the parallel job, and perform the movement. So let's create 4 variables to implement the logic: public float 3 initial position, public float 3 movement vector, so distance from the initial position, public float movement speed, which is specified in unit per second, public bool is reverse movement, which determines sign of the movement vector. It's time to implement player movement authoring. So let's begin with 2 serialized fields, one for the movement vector and the other for movement speed. Of course, prepare the getters. Then, inside the bake method, let's cache entity with transform usage flag.none and add new component, platform movement component data. Set initial position to the movement authoring.transfer.position, movement vector and movement speed from the getters, and is reverse movement to false. Normally we would move on, but in this video I also want to show you how onDraw Gizmos and handles work in practice. There are 2 Unity methods: onDraw Gizmos, which draws objects in the scene view all the time, and onDraw Gizmos selected, when an object is selected in the hierarchy. We are interested in the first one. Let's add using Unity Editor with if Unity Editor preprocessor directive, because we don't want to have any problems when we build the application, and this is supposed to be just a helpful tool for level design. Let's also create an onDraw Gizmos method, again with if Unity Editor. We want to draw the movement outline of our object, so we need a color. Let's set it to 0.4, 0.4, 0.9. Next, we need to cache the initial position with transfer.position and set a start and end point it as initial position plus or minus movement vector. With all this in place, we can use the handles library to draw a Bezier curve of the specified width. The reason I use handles to draw a straight line is that there is no direct line thickness change in Gizmos.drawLine, which is quite annoying. I also want to add wire platform shape, so I call getComponentPhysicsShapeAuthering to get the size. Add required component PhysicsShapeAuthering. Then platform size equals shape.getBoxProperties.size multiplied by transfer.localScale. Now I want to draw the wire cube, but for that I need to change the color to the visualization color. So let's write cache color equals handles.color, then handles.color equals visualization color. Next, we draw our feature at the start and end points with the given platform size. And we restore the color to the cached value. Great, time to implement platform movement system. In onUpdate, we need the delta time, which we get from system API time.delta time. Now it's time to prepare the player movement job. Let's add two input parameters, ECB ParallelWriter and delta time. Also in the execute method we'll need int sort key with the chunk index in query attribute. An entity whose components we will modify, ref local transform to get and set the position, and ref platform movement component data, where we will toggle the isReverse movement state. Let's cache three variables in the method implementation: initial position, movement vector, and movement speed. This will tidy up the rest of our code. Next, we need to determine the direction. This is a simple task, just check for isReverse movement, and if yes, set -1, and if no, set 1. The target position is the initial position plus direction multiplied by the movement vector. Then let's prepare movement step. This is the direction of the movement multiplied by normalized movement vector. It is the normalized distance to move multiplied by movement speed and delta time. This allows us to save new position as the old position and add movement step. Next, if the movement is reversed, let's check with the mat.all function whether all bool free values obtained after checking the condition new position less equal target position are true. If so, we get the true state. Similarly, in the other direction, we just change the sign. As a result, we can write if should reverse movement, and pass the three necessary parameters: sort key, entity, and ref platform movement component data. So let's create a new method, burst compile private void reverse movement, int sort key, entity, ref platform movement component data, platform movement component data. Let's modify platform movement component data isReverse movement to the opposite state and set the component via ECB ParallelWriter. Okay, back to the execute method. Let's assign new position to the local transfer.position. Then set component via ECB ParallelWriter. That's it. Let's go back to the update function and copy the getEntityCommandBuffer method from another ISystem. Remember to implement missing require for update. Next, we want to run our parallel job, so let's write job handle equals new platform movement job and pass the necessary parameters. It is EntityCommandBuffer and delta time. Of course, we'll call schedule parallel and pass the state.dependency. Finally, let's call jobHandle.complete. Alright, let's go to the Unity editor, wait for the compilation process to finish. First of all, let's create variant prefab based on the ground prefab. Let's call it ground up down movement, and inside it, add a new platform movement offering component, and let's choose some parameters. As you can see, the positions of the gizmos are updated correctly as I change the parameters. It's time to modify level 1 prefab, so let's select it. Add our newly created prefab, ground up down movement, and position it on the scene. Okay, everything prepared, so let's play the game. As you can see, the platform moves, but the player doesn't snap to it. We'll fix that in the next video. Hello TaleForge. In this video I want to show you how to snap player to platform via Unity ECS system. So let's dive in. The plan is as follows. Handle snap on the side of the independent snap player to platform system, and that's all. We have all necessary components to implement this feature. First of all, let's add the new public field EntityCommandBuffer in the player movement component data. Then we can go to the player aspect and create new getter and setter for ground hit entity. We'll set it from player detection system, so let's go to the system. Inside it, let's extend handle ground collision detection method, create new native list, distance hit, hits, new native list, distance hit, allocator.temp job. Let's change invocation from checkbox to overlap box and pass ref hits to function. We need to check if the player is grounded. If so, assign hits at index 0.entity to the player aspect ground hit entity. Don't forget to dispose hits. We don't want any handling allocations. Okay, it's time to create a new ECS system. Call it snap player to platform system. Let's add partial keyword to the struct and implement the ISystem interface. Next, add onCreate, onUpdate and onDestroy methods. With burstCompile attributes, of course. Then add two attributes to the struct, also burstCompile and update in group type of simulation system group. This system should work after all other working systems, so let's write order last equal true to ensure it. Okay, let's copy paste get EntityCommandBuffer method from another system. Note, I've wrote ECB utils to do this, which I will implement at the end of the course. They are in general code refactoring, so I will explain how to work with it. In the onUpdate method, let's write var player component data equals systemapi.getSingleton player component data. We need to check if player is dead. If so, return. The same goes for the isGrounded state. We only want to change the player velocity when we are on the ground, not in the air. Now let's cache player movement component data, ground hit entity to local variable. It will increase readability. Let's check. We want to be sure that our ground element is moving platform. If not, return. Now let's cache platform movement component data via systemapi.getComponent. At this point, we are sure it is moving platform and we want to schedule the job. Job handle equals new snap player to platform job, pass two parameters, ECB, get EntityCommandBuffer ref state, and platform movement component data. Then schedule job, pass state.dependency. After that, let's call job handle.complete, so we can wait for the job to complete. It's time to implement job then. Let's create a new burstCompile public partial struct snap player to platform job, which implements IJobEntity. Add two public fields, EntityCommandBuffer and platform movement component data. In this case, we don't need ParallelWriter. A single thread is enough for this operation. So let's implement execute method, pass in entity player entity, ref physics velocity, and player aspect. If movement direction is not 0, then we are moving, so let's return. I only want to snap to the player when it is standing still. Our direction is math.normalize player movement component data.movement vector. However, if its reverse movement is set to true, we need to change direction to negative. Okay, so now we can cache platform speed from component data. Let's assign platform speed multiplied by direction to the physics velocity.linear. Remember to set component. Without it, our change to the player velocity will not propagate. Okay, that's all. Let's check if everything is working in the Unity editor. Wait for the compilation process to finish and press play. Let's jump to the moving platform and Snap is working as expected. Great job! Hello TaleForgers, in this video we discuss the plan for upcoming videos on the enemy system, how to clean up managed components, and lay the fundamentals for systems that support two types of enemies, moving and jumping. We will be set the enemies on a level scene, so the spawn position is determined directly. Okay, so let's dive in and see how to implement this. First of all, let's create new script called EnemiManageComponentData. Inside it, we want to store three variables: public game object, transform, and animator. It will allow us to bypass ECS limitations with animations without using some third-party asset or some complex own system. In this case, let's derive from ICleanupComponentData, so our cleanup system will do the cleanup after entity destroy. We will also need to keep enemy visualization, so let's add new component data class. This time let's derive from IComponentData. Here add public game object field. Let's prepare some basic component data for our enemies, so moving enemy component data struct with field movement speed. Also, let's create component data for other enemy. So jumping enemy component data struct, and inside it we can add jump force field. It will be helpful later. Also, I did a small mistake, so let's go back to the moving enemy component data and change class to struct. So finally, after creating all necessary component datas, we need to create enemy offering class. It will have our enemy visualization game object, so serialized field and getter. Also, let's prepare enemy baker class with bake method. Here we want to get entity with transfer usage flags.none and add component object, enemy visualization component data, so we are able to handle manage type, so animations, via ECS. Pass offering.enemy visualization to game object and rename game object to enemy visualization for clarify. Since we are at the fundamentals, let's create moving enemy offering. In this case, we need a parameter to specify the speed. As before, let's create a baker. And in the bake method, after retrieving the entity, let's add a new component, moving enemy component data, and pass the parameter movement speed. Also, let's prepare jumping enemy offering. It is exactly same process with only other types, jumping enemy component data and variables, jump force. So I will do it in the fast forward. That's it. We can focus on the enemy visualization system, in which we will spawn enemy visualization and attach managed component data to have full control over animator. So let's create new ISystem, enemy visualization system. Of course, with update in group type of simulation system group attribute. Then let's prepare onCreate, onUpdate, and onDestroy methods. Now it's time to add enemy entity query variable and assign it in the onCreate. Enemy entity query equals SystemAPI.queryBuilder with all enemy visualization component data, with non-enemy managed component data, and call build. Remember to add state.requireForUpdate enemy entity query. Okay, so let's handle spawn logic. Inside onUpdate, let's create native array entity enemies equals to the enemy entity query dot toEntity array with allocator.temp. Now for each enemy entity, we need to get component object, enemy visualization component data, and instantiate game object. Here we need to modify transform.position for spawn object, so SystemAPI.getComponent local transform entity.position. Last thing to do, let's add component object via state.entityManager, pass entity, and new enemy manage component data with parameters gameObject, transform, and getComponentAnimator. Okay, but what if we want to change level and destroy entity? It is a good question. We need to clean up our enemy managed component data, so ICleanupComponentData manually. Let's create new ISystem enemy managed cleanup system. Here, also create onCreate, onUpdate, and onDestroy methods. Add new private entity query, enemy manage entity query variable. It will let us to determine if enemy entities are destroyed or not. Inside onCreate, let's write state.requireForUpdate and simulation EntityCommandBuffer system.singleton because we need to use ECB to propagate changes. Then let's assign to enemy managed entity query SystemAPI.queryBuilder with all enemy managed component data and with non-local transfer because destroyed entity don't have transfer component. Of course, build and let's add requireForUpdate and pass query. Inside onUpdate, let's cache enemies from entity query with allocator.temp. Then declare and assign EntityCommandBuffer, so write ECB equals getEntityCommandBuffer ref state. Let's go to player movement system and copy getEntityCommandBuffer method, paste it to our system, and let's create a for each entity in enemies, then cache enemy managed component data via System API. Now we can write object.destroy and pass enemy managed component data.gameObject. At the end, remember to remove component via ECB. Let's create moving enemy AI system. It will only contain debug.logs. We'll focus on this system in the next video, but for now, it will allow us to check if enemy visualization system is working correctly. First of all, let's create basic methods and prepare entity query, enemy entity query. In the onCreate method, assign query with all enemy managed component data and with all moving enemy component data. Don't forget to add state.requireForUpdate enemy entity query. Inside the onUpdate function, let's write debug.log moving enemy AI system, then cache enemies to the native array entity with allocator.temp. Let's create for each OR entities and log entity.index. Next, let's retrieve enemy managed component data via state.entityManager.getComponentObject. Remember to pass entity. Then we can debug.log animator, GameObject, and transform to check if everything is working properly. That's it. Next, let's create jumping enemy AI system. We can copy moving enemy AI system code and paste it to the jumping enemy AI system. Let's change type in the query builder to the jumping enemy component data. Also change text in the debug.log. And that's enough to test if system is correctly operating. So it's time to go to the Unity. My graphic designer has prepared sprites and I have created animation clips and animator controllers. As you can see, I have iGlue and move animations for the moving enemy and iDo and jump for the jumping enemy. Simple as that. First, let's create new directory in the prefabs, call it enemies. So let's prepare enemy visualization prefab. First of all, create empty game object and name it enemy visualization. Drag and drop it to the project tab. Then let's add sprite renderer and animator components. Also, let's change scale to half. I tested it before and scale 1 was so big for these enemies, they were really huge. Okay, now let's create prefab variants, moving enemy visualization and jumping enemy visualization. In the moving enemy visualization, change sprite to the moving enemy and animator to the moving enemy animator controller. In the jumping enemy visualization, set sprite to the jumping enemy and animator to the jumping enemy animator controller. Now it's time to create enemy prefab, so prepare empty game object, then drag and drop it to the prefabs folder. Inside this prefab, let's add 3 components: enemy offering, physics body, and physics shape. In the physics shape, let's change the size and bevel radius to these values. Then let's change the collision filter settings. Set belongs to as enemy, so 5th index. We need to add new layer to the physics category tags and collides with to player and ground. Also set mass to 10. Okay, let's create 2 prefab variants, moving enemy and jumping enemy. In the moving enemy, attach proper enemy visualization and add moving enemy offering component. You can also set some parameter, let's say 2. In the jumping enemy, also attach proper enemy visualization and then add jumping enemy offering with parameter jump force set to 10. Next thing to do, inside ground prefab, we need to add enemy layer in the physics shape, so enemy will not fall into void. Let's change collides with and add enemy layer here. Okay, let's open level 1 and position 2 enemies. It doesn't matter where I will place them for now, because I will change it in the next videos. The most important thing is to place both moving and jumping enemies to test our systems. Everything is ready to go, so let's press play and test if our enemies spawn at the right position and we get correct debug.logs. As you can see, everything works fine. Good job! Hello TaleForgers! In this video we'll implement the first type of enemy, the moving enemy, which will patrol the platform. When it reaches an edge, It will wait for a moment, so idle, and turn back until it reaches the next edge. So let's dive in. Let's start by creating an enum that has two states, namely idle and move. We'll use this enum to implement logic in the moving enemy AI system. Now open moving enemy component data, and inside it let's create new fields: public double idle time to store the idle duration, idle finish time to set this time inside system and check if idle is finished. Also moving enemy state to determine what state the enemy is currently in. And the last one, ground collision filter, to check if our moving enemy is hitting ground. Okay, so create new serialized fields for the new variables: double idle time and two fields to store the physics category tags: ground belongs to and ground collides with. Of course, let's prepare getters for the idle time and collision filter, which is created from two other variables. In the bake method, we need to pass additional data to the moving enemy component data. Before we go any further, let's remove unnecessary debug.logs from the jumping enemy AI system. Same operation for the moving enemy AI system. Great. We need to modify local transfer and read properties from the physics collider. So let's add these types to the query builder in the onCreate. Next, let's copy and paste getEntityCommandBuffer from other ISystem. Also, let's add missing require for update. Let's cache EntityCommandBuffer and pass ref state. We want the operation to be correctly queued in the EntityCommandBuffer, especially since we will be executing them in the for each. So let's write var moving enemy component data equals state.entityManager, get component data, moving enemy component data, and pass entity. Then cache local transfer, also via entity manager. Before we move on, let's create 5 new methods. We'll use them in a moment. Firstly, create private unsafe bool is grounded with parameters ref system state, moving enemy component data, entity, and local transfer. Next, prepare private void move, ref system state, enemy manage component data, moving enemy component data, entity, local transfer, and entity command buffer. Quite a lot of parameters, but we will need them all to handle our movement correctly. Then let's prepare private setMove method with same parameters as the move function. Our forward method, idle, will have exactly the same parameter list. In the case of the setIdle method, we have almost the same parameter list, just remove local transfer. Okay, let's go back to the onUpdate and check condition. If moving enemy component data.state is equal to move state, we want to move enemy to the next position. So let's call move and pass all necessary parameters. Then let's check if our enemy is grounded. If yes, continue. But if not, he will fall into the void of the eternity. Just kidding. We will prevent that with setIdleState and call continue, so we will end this iteration early. At the end of the method, let's call idle method, which will wait for the idle time. Okay, it's time to implement isGrounded function. First of all, we need to cache collision word because we want to cast ray to detect ground. Remember to add missing require for update. Next, cache local transform position. After that, we need to store physics collider, so state.entityManager.getComponentData physics collider and pass entity. As you can see, we have unsafe keyword in the method. It will be helpful in the case of the next operation. It as var box collider equals box collider pointer physics collider.collider pointer. From box collider, we can retrieve box geometry, which will be useful to get half extents geometry.size divided by 2. Finally, we are able to calculate x shift, so half extents.x multiply math.sign moving enemy component data.movement speed. We need to multiply it by the sign so that our detection will change direction when the enemy changes movement side, left or right. Let's create a RayCast input with input parameters. Start equals new float 3 position.x plus x shift position.y position.z. End equals to the new float 3 position.x plus x shift position.y minus half extents.y multiplied by 2 position.z. And of course, filter from the moving enemy component data. I have multiplied half extents by 2 to increase array length. It can be 3 or other value as long as array length is not too short or too long for detection. Let's return collision word.cast raycast input, so it will return bool, true equals hit, or false, which means no hit. Okay, it's time to implement move method. We need to calculate a new position, float 3 position, equals to the local transfer.position, so current enemy position, plus moving enemy component data dot movement speed multiplied by system API.time .delta time multiplied by direction vector. It is simple new float 3 1 0 0. Of course, let's set component data via ECB and assign new position to the managed object. And that's it. Now in the setMove method, we need to set bool move to the true and state to the move state. Remember to set movement speed to the opposite value. Then we need to set component to propagate changes. Last thing to do, let's rotate our enemy by 180 degrees in the ECS and the mono representations. Of course, don't forget to set local transfer component. idle is a short function. We need to calculate the difference between idle finish time and elapsed time from the system API. If this difference is less than or equals 0, we call setMove method. We need to implement one last method, setIdle, in which we set animator move state to the false, enemy state to the idle, and set idle finish time to the system API.time.elapsed time, plus moving enemy component data.idle time. Of course, remember to call ECB.setComponent. Let's rename EntityCommandBuffer to the ECB. Okay, go back to the Unity editor, wait for the compilation process to finish. It's time to modify enemy prefab. Let's change physics shape size x and y to 2. Previous values were too small to correct working. Next, let's remove PhysicsBody component in the moving enemy. It is unnecessary for the linear, simple movement. Don't forget to adjust parameters, set movement speed to 2 and idle time to 1.5. Then we need to select the correct belongs to and collides with parameters in order enemy and ground. During testing, when I was preparing the material, I noticed that the visualization was reversed 180 degrees. So let's correct it inside moving enemy visualization prefab. Okay, so let's go to the level 1 prefab so we can adjust moving enemy position, and also let's remove this collectible for now. Great, let's test if everything is working properly. So click play and as you can see, our enemy is moving from one end of the platform to the other. Awesome! Hello TaleForgers! In this video we'll implement the second type of enemy, jumping enemy. It will hide for a moment and then jump. So let's dive in. Let's start from the code. First of all, create jumping enemy state enum with two states, idle and jump. Inside our jumping enemy component data, we need to add some variables. It is public double idle time, public double idle finish time, public jumping enemy state, and public collision filter, ground collision filter. This data will be necessary to implement jump and idle actions. So let's go to the jumping enemy offering. Here let's add 3 new serialized fields, 1 for idle time and 2 for the collision filter. So ground belongs to and ground collides with. Of course, don't forget to create getters for these variables. Then, in the bake method, let's pass these parameters to the jumping enemy component data. Finally, we can implement jumping enemy AI system. Let's start with adjusting entity query. We want to add physics collider because we need to detect collision with the ground. Next, physics mass and physics velocity to apply linear impulse, so our jump. And local transfer to synchronize manage component position with entity current position. Also, let's add state.require for update for physics word singleton and end simulation EntityCommandBuffer system.singleton. Then let's copy and paste get EntityCommandBuffer from the moving enemy AI system and cache it in the onUpdate method. Before we move on, I want to implement all methods. So let's copy and paste is grounded from the moving enemy AI system. For now, let's just change moving enemy component data to the jumping enemy component data. And also remove X shift for this case. Is grounded method could be exposed as a utils function. In the refactor at the end of the series, I will polish this code. Let's adjust a value of the Raycast input end, so change to f to 1.5f. Next, let's create new method, private void sync manage position with 2 parameters, enemy manage component data and local transform. We want to simply set enemy manage component data.transfer.position to the local transform.position. Then let's implement idle function with ref system state, jumping enemy component data, enemy manage component data, entity, ref physics velocity, in physics mass, and entity command buffer. First of all, let's cache time to end idle state, so jumping enemy component data.idle finish time minus system API.time.elapsed time. So if time to end idle state less equals 0, call jump and pass all necessary parameters. We will implement jump method in a moment. Now let's prepare set idle method. We need 4 parameters: ref system state, jumping enemy component data, entity, and EntityCommandBuffer. Inside this function, let's change enemy state to the idle. Then calculate idle finish time. It is system API.time.elapsed time plus jumping enemy component data.idle time. Remember to call ecb.setComponent to propagate changes. Finally, it's time to implement jump method. We need jumping enemy component data, enemy managed component data, entity, ref physics velocity, in physics mass, and EntityCommandBuffer. First, call enemy managed component data.animator.setTrigger jump, so our animation will start working. Second, change enemy state to jump. Of course, set jumping enemy component data via ECB. We want to apply our jump force to the enemy, so let's call physics velocity.apply linear impulse. Pass physics mass and new float 3, 0, jumping enemy component data.jump force, 0. Remember to set physics velocity component data to make our changes take effect. Now let's go back to the onUpdate, and inside for each we want to cache via state.entityManager.getComponentData, jumping enemy component data, physics velocity, physics mass, and local transform. I want to sync manage position, but only when enemy is during jump. So let's check if mat.length_square physics velocity.linear is greater than 0.1. If so, update position and continue. Then, if enemy is not grounded, continue. Finally, if our enemy state is equal to jump, we can set state to idle because he just finished jump action. At the end, let's call idle method with all the necessary parameters so enemy can wait for idle to finish and start jumping again. Okay, it's time to return to the Unity editor. We need to set parameters in the jumping enemy prefab. First of all, let's change jump force to 100 and idle time to 2. Next, let's set ground belongs to the enemy and ground collides with to the ground. In the physics body component, let's set inertia to the infinity. We don't want our enemy to randomly rotate by a few degrees after the physics calculations, so we freeze rotation. Okay, let's press play. Go to the level scene. As you can see, our jumping enemy is working as expected. Awesome! Hello TaleForgers! In this video I want to show you how to implement generic functions in Burst with Unity ECS system. So let's dive in! Okay, so let's start by creating an enemy type enum. We'll use it in this tutorial to assign a type to an enemy, and in the next video to determine how much damage a given enemy has dealt. Let's add 3 values: none, moving, and jumping. Next, we need to implement our enemy component data. In this component, we want to add enemy type field, which will allow us to handle damage dealt by the enemy in the system. Of course, we also need to modify enemy offering. We simply add serialized field for the enemy type with a getter. Then we add enemy component data and pass the type from the offering class. Okay, it's time to go to the Unity editor. We want to set types for moving enemy and jumping enemy prefabs. So let's do it. This will allow us to distinguish our enemies. After that, return to IDE, select player component data. In the next video, we want to set player health. That's why we need to add public float health field. Obviously, it is necessary to set this variable initial value in the player offering. So let's add serialized field private float health with a getter. And remember to pass value in the player baker. Great! Now we can focus on the player detection scripts. Let's begin with player detection component data, in which we would like to add enemy collision filter. Then, inside player detection offering, let's create new serialized field, physics category tags, belongs to, and collide with for our enemy. As before, we need to create a collision filter consisting of both tags. Don't forget to pass enemy collision filter in player detection baker. Okay, go back to Unity, recompile. Let's go straight to the systems, select player detection game object. For the enemy belongs to, set player, and for enemy collide with, enemy. This way our player will collide with enemy and receive damage. Fantastic! It's time to return to Rider. This system still uses obsolete aspects. Let's just add enemy collision filter to it. Finally, we can implement player detection system. Let's create a member variable for enemy collision filter and assign it in the onCreate method. Remember to pass it in the player detection job. It's time to implement our generic method. First of all, we can delete handle collectible collision detection method and create a new private void handle generic detection for many hits. Of course, with base compile attribute. It is generic function, so let's add t and prepare parameters, local transform, player transform, box geometry, and collision filter. The most important part is to specify t generic parameter, so let's write where t unmanaged because it is struct IComponentData. Without where, we cannot use ecb.addComponent entity new t later in the code, because somebody can pass, for example, a class, but addComponent only accepts unmanaged code, which is IComponentData. Now, prepare native list distance hits with allocator.tempJob. We can write bool is collision equals our overlap box method with player transform, box geometry, ref hits, and collision filter parameters. If is collision, for each every hit, and add component via ECB. Our component is new T, where T is determined in the where block. At the end, don't forget to dispose hits. Next, we need to call this generic method, so let's adjust handle collectible collision detection to use handle generic detection for many hits. And also do it for enemy detection, but with parameter player damage component data, which we will create in a moment. Note the way parameters are passed, especially inside T notation. Great, we have prepared our enemy detection. Now let's prepare player damage component data and player damage system that we will use for debug.log today. And later we will use them when actually dealing damage. So let's create player damage component data, which is order flag for the player damage system. Next, prepare player damage system. It is ISystem struct with burst compile and update after type of player detection system attributes. Firstly, let's implement onCreate, onUpdate, and onDestroy methods. With burst compile attribute, create new entity query, damage entity query variable. Inside onCreate, we want to assign our damage entity query via system API.queryBuilder. With all player damage component data .build. Don't forget to add state.require for update damage entity query. Then, in the onUpdate function, let's cache damage entities via toEntity array with allocator.temp. Just for now, I will add debug.log damage and dispose damage entities array. Okay, let's go to the Unity, select main scene and press play. Start game and collide with enemy. As you can see, our enemy detection is working properly. Hello TaleForges! Last time we implemented a generic function and prepared collision detection. Today we'll focus on player life management and UI. Thanks to the component-based approach, we can use the player dev logic without having to implement a separate system. So let's get started. First, we need to create enemy SO, which obviously derived from ScriptableObject. Here, we'll keep enemy type and damage. We want to select it via Unity editor menu, so let's add create asset menu attribute. As I did with the BlobAssets video, we want to transfer data directly to ECS via blobArray. That's why we need to prepare enemy container with same fields as enemy SO. This struct will be used as data container by enemy pool. So let's create a new struct, name it enemy pool and add blobArray with enemy container. It is our enemy's data, which will be called from Burstable ISystem. Last thing to do, we need to store our BlobAsset reference somewhere, so prepare enemy's component data, which implements the IComponentData, and create a public variable for it. Great, our data is ready to go. However, it is necessary to communicate mono-SO with ECS, because we want to use Burstable ISystem, not manage SystemBase. That's why our next struct is enemies offering. In this mono behavior class, we'll have one serialized field, list, enemy SO, and getter for Baker. So let's prepare enemies baker class, which derives from baker enemies aferin, and implement bake method. Okay, now we can get entity with transnode usage flags.none. Then prepare the create enemies BlobAsset method, which returns a BlobAsset reference enemy pool and takes an iRead-only list enemy SO as a parameter. It's time to create our blob builder with allocator.temp and using. It will be automatically disposed at the end of the scope. So let's construct root for our enemy pool. This pool will be used for blob builder array. Let's allocate ref enemy pool enemies data with length enemies data.count. Now we need to iterate over all enemies data, cache necessary parameters, it as enemy, enemy type, and damage. Let's write array builder at index equals new enemy container with parameters enemy type and damage. At the end of the method, call builder.create BlobAsset reference enemy pool with allocator.persistent. We want our data to be stored permanently. Finally, go back to bake method to call our create enemies BlobAsset with enemies SO as a parameter. Then let's add BlobAsset ref enemies BlobAsset out discard. At the end, add component enemies component data and pass enemy pool reference. It's time to set our data in Unity. We can prepare enemies directory and then create two enemy SO, one for moving and one for jumping enemy. In the case of the moving enemy, I want to set damage to 1 and in the case of the jumping enemy to 2. This way, after hit 1 moving and 1 jumping enemies, we can test our loss gain trigger. Player health will be equal to 3. Okay, let's go back to code. First of all, let's copy and paste get EntityCommandBuffer code from other ISystem. In the onCreate function, let's add missing require for update for our EntityCommandBuffer. After that, let's prepare Burst compile private void execute damage logic method with parameters ref system state, native array entity damage entities, and index ref blob array enemy container enemies data and entity command buffer. First, let's cache damage entity and enemy component data via system API. Let's implement for after all enemies data. Then cache our enemy container and check if type is equal to the enemy component data type. If so, destroy damage entity via ECB and create health entity via state.entityManager.createEntity method. Let's add health component data, we'll create it in a moment, with value set to the minus enemy container.damage. At the end, break to minimize number of operations. We need to prepare health component data. It is iComponent data with value to heal or to damage depending on the context. Now let's go back to the onUpdate method in which we cache blob array enemy container in similar way that we did in the BlobAssets tutorial. Link to the video somewhere on the screen. Check it out. Don't forget to add require for update enemies component data. And we can go through all elements in damage entities and execute damage logic. That's all in this system. Now let's create health system class. It is an SystemBase responsible for communication between Mono and ECS. Of course, implement missing on update method. Then create public event action float health updated. This will allow us to communicate with the Mono behavior health UI. To ensure that execution order is correct, we can add update after attribute with player damage system type. In this system, we need to add two variables: entity query, health entity query, and level system reference. Obviously, let's build health entity query with health component data. We also need to add require for update player component data. To handle health points UI update on the level loaded, let's create onStartRunning and onStopRunning methods. In onStartRunning, we need to cache level system via EntityManager.word.getExistingSystemManageLevelSystem. This way, we can subscribe to level loaded event. Similarly, in the onStopRunning, let's unsubscribe from this event. Okay, it's time to implement onLevelLoaded. As you can see, AI knows better what I want to do. Let's correct signature. Let's simply cache player component data to local variable and invoke health updated event. In this case, our AI assistants did really well. Last thing to do, we need to handle player health update and death state. So let's cache health entities and health component data array with allocator.temp. Also, player entity and player component data via system API.getSingletonEntity and getSingleton respectively. Let's iterate for every health component data, cache health entity and health component data, update player health via health component data.valueAmount, and destroy needless entity. Next, if player health is above 0, let's set isDeadState, and our lost system will automatically trigger. Then propagate changes via EntityManager.setComponentData. Don't forget to dispose native arrays. I'm really impressed by how autocomplete works in new Rider version. It's huge improvement. Great! Now let's do one micro optimization. Go to the point system and move pointsUpdated.invoke points outside of the for loop. So let's go back to Unity. Go to the systems prefab, create empty game object enemies and attach new component enemies offering. Let's add two elements to the list, moving and jumping enemy SO. Okay, it's time to implement health user interface. Let's start with code. Let's create health folder and inside it health model monoBehavior class. All we need to do is add a reference to TextMesh Pro. After all, we want to update the state in the user interface, right? Next, create health view monoBehavior class with attribute required component type of health model. Let's prepare health model variable so we can, in update view method, set text to the current player health points. As we don't use serialize field here, don't forget to add private void awake function with getComponent health model to cache member variable. Our last script to implement is health controller, which will know about health model and health view. So, add required component attribute with both components. Then prepare member variables for model, view, and also for health system. We will communicate via it with ECS system. In the private void awake, we will cache our variables via getComponent and health system via word.defaultGameObjectInjectionWord.getExistingSystemManageHealthSystem. So let's add on enable and on disable methods to subscribe unsubscribe from health updated event. And finally, let's implement last function in this video. Private void on health updated float health, inside which call healthView.updateView points. That's it. Let's go back to Unity, select game scene, and open canvas game object. Let's duplicate points and rename it to the health. Set anchor to right corner and adjust position, width, and height accordingly. Also remove point scripts and add health controller. Thanks to required component, it will automatically add health model and health view. Drag and drop reference to the health text field, then rename points text to health text and set value to health. Great! To prevent player movement jobs schedule jobs before previous one ends, let's add job handler and state.dependency. At the end, call jobhandler.complete. It will prevent any race conditions for EntityCommandBuffer in the case of the player component data. Last thing to do, let's set player health to 3 points so we can test our death trigger. During tests, I noticed I did one pretty nasty to find bug. Required for update damage entity query in the player damage system need to be called after query builder. Otherwise, it will be null reference. Then, let's go to the main scene and press play. We need to find an enemy and jump into it. Here is one. As you can see, we lost 1 health point. Now let's go to the second enemy. Yeah, we lost game. Fantastic. Hello TaleForgers! Ever wondered how AAA games manage thousands of characters, physics, calculation and AI without slowing down your game? The secret might just be Unity ECS. In today's video, we are diving into what ECS is, why it could be the future of game development, and the pros and cons you need to know. So let's dive in! Everyone loves examples, right? The V-Rising development team used Unity ECS to handle massive server-side simulations, destructible environments, and thousands of networked entities efficiently. Ixion, for instance, used ECS to manage numerous dependencies for game events and data. They also handle UI events with high performance using cache entity queries. In the case of the Diplomacy is not an option game, Sergey Klimenko, lead developer, says, "We are using dots almost everywhere in our game, and we are finding it especially useful for pathfinding and optimizing our gameplay logic." Okay, but what exactly does ECS mean? Some of you, who have been watching me for a while, probably remember my old video about it, but let me quickly recap for the new viewers. ECS stands for Entity Component System, a data-driven approach to game architecture. Entity, think of it as a game object placeholder. Component holds data only, no behavior. So position, health, speed, you name it. System executes logic on our components, movement, rendering, AI, etc. Traditional Unity use OOP with monobehaviors, but ECS is optimized for performance and parallelization. That means your CPUs work smarter, not harder. So why is ECS a game changer? Here are the main advantages. Massive performance boost, process thousands of entities efficiently using CPU multithreading. Memory efficiency, components are stored next to each other in memory, which makes access much faster. Scalability, easy to manage huge worlds and large numbers of objects. Predictable behavior, systems are decoupled from data, making bugs easier to isolate. Perfect for procedural simulation games like crowd simulation, RTS games, particles effects, or complex AI. Of course, nothing is perfect. ECS has a few drawbacks. Steep learning curve, data-oriented programming is very different from traditional OOP. Less documentation and tutorials. ECS is still evolving, so finding answers can be tricky even with AI. Not always necessary. For small games, mono behavior might be faster to implement, so ECS is amazing for performance CV projects, but it's overkill for a simple mobile game. Alright, let's quickly recap what we have learned in our ECS series. We started with the basics, entities, components and systems, the foundation of data-driven game development. Then we dive into randomization, learning how to efficiently add randomness to thousands of objects. Next up was movement and input. We smoothly moved bullets and other entities using ECS and also controlled the player using the new input system. We tackle physics and collisions, jumps, grounding and enemy interactions, all running perfectly without slowdowns. Next up, animations at scale. Manage components, skin meshes, thousands of animated objects, plus the Rukhanka animation system. We communicated the UI with ECS via SystemBase, showing how to build windows and handle events, and also covered the basic of animation using DOTween. We also covered scenes and subscenes with loading screen, keeping huge projects organized. We optimize how we store and share data in ECS for ultimate performance. BlobAssets lets us store large amount of immutable data in memory for fast access, while ScriptableObjects help us configure and reuse that data across entities without duplication. Then came the high-performance techniques, burstable functions, compute shaders, and insane simulations, like over 691,200 entities or 10,000 skin mesh renderers running at the same time. And finally, the cherry on top, advanced ECS integrations, combining ECS with compute shaders to offload heavy calculation to the GPU for insane performance, and VContainer with ECS to keep dependency management clean, scalable, and maintainable for complex projects. Which of these topics blew your mind the most? Or which one was the trickiest to implement? Drop your thoughts in the comments. And that wraps up this ECS series, a nice summary of what we have covered so far. ECS is a huge topic, so there is always more to explore, and I might share new tutorials or other materials in the future. Stay tuned! I would like to invite you to support us on the Patreon, where you can get the exclusive code, all models, materials or code used in this series, and access to early available content. Link in the description. Thank you for your time, I'm glad you are with us and our community is growing. See you soon in the next video. Hello TaleForgers, at your request I have prepared a tutorial about bad apple in Unity ECS. To begin with, what interesting topics will be covered? First, we'll focus on the quad spawner. The created matrix will be used for display. Second, we will create a system responsible for the logic. It will be SystemBase with managed component data. Of course, we will also create a shader, a prefab, a scene, and everything will communicate with each other, and this is where new things come in. So this tutorial will be a kind of summary of what has already appeared on the channel, as well as some new, I think, interesting things. So let's dive in and see how to create BlobApple in ECS. Let's start with the code part. As you can see, I have created all the necessary files to just write code. You can pause video and also create empty files with class definitions. Let's start from BlobApple spawner component data script, change class to struct, and implement IComponentData interface. Of course, add using Unity.entities. Now we need to add 4 fields: public entity visualization, public int render texture width, public int render texture height, and public bool is spawn complete. There I created 2 classes, one for authoring and one for baker. As you can see in baker, I have derived from the baker BlobApple spawner authoring class and override the bake method. In the authoring we need to add 2 serialized fields. BlobApple visualization, it is prefab, we will create it later, and render texture. Of course, prepare getters for fields. In the baker class, we need to get entity with transfer usage flag.none. Add component, entity, new BlobApple spawner component data, and pass parameters through the constructor initialization. Visualization equals get entity spawner authoring.BlobApple visualization transfer usage flags.renderBoo. RenderBoo is enough because we don't need to move entity. And pass render texture width and height. In BlobApple spawner system, I added burst compile attributes, change class to partial struct, and prepare onCreate, onUpdate, onDestroy, and empty BlobApple spawner job. BlobApple spawner system implement ISystem, and BlobApple spawner job implement IJobParallel4. First, we want to get the singleton entity for BlobApple spawner so that we can retrieve BlobApple spawner component data. Of course, add require for update. Then, check if the isSpawnComplete parameter is set to true. If so, return early. Now we need EntityCommandBuffer to handle spawn operations in job. So let's add private method EntityCommandBuffer.ParallelWriter, get EntityCommandBuffer, ref SystemState, and inside var ECB singleton equals to SystemAPI.getSingleton and simulation EntityCommandBuffer system.singleton. Also add require for update and return ECB.singleton.createCommandBuffer state.wordUnmanaged.asParallelWriter. Next, let's cache the texture width and height, as they will be useful for setting the array length for IJobParallel4. Now let's implement BlobApple spawner job. Add 3 public fields: public int render texture width, public entity BlobApple visualization, and public EntityCommandBuffer.ParallelWriter ECB ParallelWriter. In the execute method, let's instantiate BlobApple visualization. Remember to pass sort key. Then calculate row and column. Row equals to sort key modulo render texture width, and column equals to sort key divided by render texture width. Simple as that. Now set component via ECB ParallelWriter, pass sort key, BlobApple visualization entity, and new local transform, position is equal to new float 3, row, column 0, rotation to quaternion identity, and set scale to 1. So go back to system and let's write job handle. Job handle equals new but apple spawned job, open brackets, and pass render texture width, visualization, and EntityCommandBuffer. Of course, schedule, array length is equal to render texture width multiplied by height. Batch count, let's set to 64. According to documentation, for simple job, you should set value between 32 and 128. And pass state.dependency so we can wait for job to complete. Don't forget to call jobHandle.complete. Set isSpawnComplete flag to true and set component via System API. Oh, I forgot to add BursCompile attribute to get EntityCommandBuffer. Alright, the entity spawner was successfully prepared. Now it's time to implement the logic responsible for the display. Let's move on to BlobAssetComponentData, and note, this time we leave it as a class, as it will be managed component data. We implement IComponentData and create a public field, render texture. Let's move on to BlobAssetOffering class. Let's create a serialized field, render texture, and getter. In the baker, get entity with non-flag, and add component object, pass entity as first parameter, and new BlobAssetComponentData with offering.renderTexture as second parameter. Okay, now we need to prepare new component data, which will define the float 4 value passed to the shader. So let's go to BlobAsset visualization color component data, change class to struct, implement IComponentData, and add public field float4 value. To make this work, we need to add a material property attribute with a name of our choosing. The field name must be identical in the shader we create next. Let's call this property BlobAsset visualization color. Let's leave the offering class empty, then in the baker get entity with transformUsageFlat.none, and let's add component BlobAsset visualization color component data to cached entity, which you can also write in the generic form, and it's fine. The last thing to implement in code is BlobAsset system. In this system, I added BursCompile attributes on create, on update, on destroy, and empty BlobAsset job. BlobAsset system class derived from SystemBase, and BlobAsset job implement IJobParallel4. First, we need to create two variables: private entity query, BlobAsset visualization color query, and private entity query, BlobAsset query. Then assign queries in the onCreate method. First query get all BlobAsset visualization color entities, and second get the BlobAsset singleton entity. We are using query to get singleton entity because BlobAsset component data is managed type, so we can't use system API.getSingletonEntity. Now we need equivalent of the onEnable from monoBehavior. So let's create the onStartRunning method, and inside getSingletonEntity from BlobAsset query, we need this entity to get component object, our managed component data. Now we can write prepare frame texture and pass BlobAssetComponentData.renderTexture parameter. Of course, we want to create this method. There we prepare our texture2D instance. It has pass width, height, texture format. It is necessary to do this because, unfortunately, we can't work on the render texture to get needed data. According to the documentation, a render texture only has a data representation on the GPU, and you need to use texture2D.read pixels to transfer its contents to CPU memory. However, read pixels is very slow. That's why we want to read the texture async via async GPU readback. This is definitely a more efficient reading method. However, we will implement it in the updateFrameTexture method. Now focus on the prepareFrameTexture. Okay, let's go back to code. Let's create private texture2D field, currentFrameTexture, and in prepareFrameTexture, assign new texture2D, but APURenderTexture.width, but APURenderTexture.height, textureFormat.RGB32, false. Don't forget to add best compile attribute. Now we need a reference to render texture during the updateFrameTexture method, which we will implement later. So in the onUpdate method, we can copy-paste code from onStartRunning, but without prepareFrameTexture. But ICleanupComponentData contains this reference. Then let's create two native arrays to get BAT-APU visualization color, entity array and component data array. Set allocator to temp job. Now we want to call updateFrameTexture and pass render texture from BAT-APU-component-data. Create new method, private void updateFrameTexture with renderTexture parameter. Of course, add best compile attribute. Inside this method, we need to set renderTexture.active to renderTexture parameter. Now what we care about is async fetch data from the GPU and set texture2D located on the CPU. So let's write async GPU.request pass render texture. We can set MIP index to 0 and use lambda expression for async callback. Inside the lambda expression, we want to check if currentFrameTexture equals null. If so, return. It prevents error on application quit. Next, currentFrameTexture.setPixelData, pass async callback.getDataByte, MIP level set to 0. Don't forget to apply changes to texture. You can also set renderTexture.active to null. Great, we implemented the updateFrameTexture method, so let's go back to onUpdate. What's next? Get pixel data color 32 from currentFrameTexture and cache it into variable, pass 0 as MIP level. So it's time to implement job. We need to add two native arrays, which will have deallocate on job completion attributes. It has public native array entity, BAT-APU visualization entities, and public native array BAT-APU visualization color component data, BAT-APU visualization color component data array. Also public native array color 32, BAT-APU pixels array, which we deallocate on the onUpdate due to the fact that allocator for getPixelData is set to temp. And of course, EntityCommandBuffer.ParallelWriter ECB ParallelWriter. Let's copy-paste getEntityCommandBuffer method from BAT-APU spawner system plus remove ref system state and change state to entity manager. In the execute method, we retrieve current BAT-APU visualization color component data. Sort key is our index. Also get pixel from array and create new float for color pixel.r, pixel.g, pixel.b, pixel.a, divided by 255 shader text values from 0 to 1. And I couldn't get the getPixelData method to take color instead of color 32. Now, very important check. If ButAppleVisualization color component data.value.equals color, then return. This saves a lot of operations, especially in the case of white-black pixels. Let's assign ButAppleVisualization color component data.value with color. Then ECB ParallelWriter.setComponent sort key ButAppleVisualization entities pass sort key as index ButAppleVisualization color component data. Okay, let's go back to onUpdate method and write jobHandler equals new ButAppleJob. Pass all necessary parameters, ButAppleVisualization entities, ButAppleVisualization color component data array, pixels, and get EntityCommandBuffer. Don't forget to schedule the job. Pass ButAppleVisualization entities.length as the first parameter, then set batch count to 64 and pass dependency. Wait for the job to finish with jobHandler.complete. After that, let's dispose pixels. Finally, we have our ECS code prepared. Now it's time to add a little counter and we can go straight to Unity. Set the text at the start to entities count texture width multiplied by texture height. Also add bold to text and remove unnecessary using. So let's go to Unity and create custom shader. Right click, create, shader graph, URP, unlit shader, rename it to ButAppleVisualization shader. Let's add a new vector4 field and name it ButAppleVisualization color as in the code. Then in Graph Inspector in Node Settings, check Override Property Declaration and change shader declaration to hybrid per instance. In the graph settings, change the surface type to transparent so that we have access to the alpha channel. Now drag and drop to the field to create a node. Click on the output and use split node. Connect alpha output from split node to alpha input on the fragment node. Now let's pack the colors into vector3, right click, create node, choose vector3, and connect inputs and output. That's it! Remember to save asset. Now let's prepare prefab. Create quad object on the scene, rename it to ButAppleVisualization, reset position to 0, 0, 0. Then add component to object, ButAppleVisualization Affering. Disable cast shadows and remove mesh collider. In the mesh renderer, change material to ButAppleVisualization shader. We don't need to create new material in this case because we don't have some settings to customize. Drag and drop to project tab to make it prefab. Don't forget to remove it from scene. As you can see, I have an empty scene called ButApple. I need a render texture on which I will show the original video. So let's create a ButApple render texture, set width to 480 and height to 360. So it got 172,800 entities. You can set anti-aliasing value to 8 samples. Then let's create a new canvas. Select UI Scale Mode to scale with screen size. Set reference resolution to Full HD. Match to width. Now right click on canvas, UI, Raw Image. Rename it to ButApple Raw Image. Adjust the position, anchor and size to suit your needs, and select the render texture we made before. Also create an entities counter. Add a new TextMesh Pro component, rename the object to BlobAsset adjust position and size. Set font size to 60 and align to center. Add a script of the same name to it. Then pass necessary references. Now let's create video player. Right-click, video, video player. Of course, set the video clip and the target texture to BlobAsset render texture. Next, let's create a camera. Change position to X equals 220, Y to 180, Z to -10. Also projection to orthographic with size 180. In the rendering tab, you can enable post-processing for temporal anti-aliasing, TAA. Set quality to very high. Disable occlusion culling and render shadows to minimize camera calculations. Also set background to solid color, white. Last thing to do, create ECS subscene. Name it BlobAsset ECS. Inside subscene, let's add two objects, BlobAsset and BlobAsset spawner. For BlobAsset, add BlobAsset offering component and select render texture. For BlobAsset spawner, add BlobAsset spawner offering and select two parameters, visualization and render texture. Let's re-import the scene to see if we still get an error when we set the render texture reference. Okay, let's test if it is working. Indeed, great job! I encourage you to support us on Patreon. Even a small contribution is a huge help in creating new content. Tier 2 also gives you access to code and assets. Link in the description. Thanks for your time. I hope you enjoyed the video and most importantly learned something useful. Take care and see you soon in the next video. And now enjoy BlobAsset.
Hello TaleForges, I have something special for you. Lately, I have been playing around with compute shaders in my spare time, like in the last showcase video, and I would like to share my knowledge with you. That's why I want to show you how to implement the falling sun particles shader with ECS code. So let's dive in. As you can see, I switched to PC platform and set full HD resolution for this tutorial. First of all, let's create directory falling sun particles and ECS scripts. Draw component data, draw afferent, draw system which will control pixels, draw input system which will control input for the drawing. Also, we need to prepare enum, draw input mode. Then, after all the scripts are created, let's prepare the initial texture. I just copy and paste from my resources. It's all green color because green pixel is considered as obstacle. Red pixel will be sent particle, and black pixel will be empty space. In the inspector, let's select texture type to sprite. Also, uncheck alpha is transparent checkbox. I want to have black background. Last thing to do, let's create a new compute shader. Name it falling sun particles. Great, so now let's prepare a new scene, falling sun particles scene, in which we have to leave the main camera object, but we can freely delete the directional light. Let's modify parameters of the camera, position Z to -1. Also select background type to solid color and projection to orthographic. Let's adjust orthographic size to 1. Okay, now create a new ECS subscene, falling sun particles ECS. Here, let's add a quote. Create a new material, falling sun particles, and set it to URP unlit. This will be our display for the render texture created via code. Drag and drop falling sun particles material. So set scale on the quote. We want to remove a mesh collider from this object and use box collider to detect the raycast via ECS and change box collider Z size to half. Also create a new object, draw, and attach a draw afferent component to it. Here we need to select references and parameters later. I want to use new input system, so let's create input actions and name it draw input controls. Select the asset and check generate C# class. Then apply. Wait for the compilation process to finish. Then, inside the asset, let's create a new draw map and prepare 4 actions. Pointer position with action type value and control type vector 2. Let's choose the path to the position pointer. Space action with the path space keyboard. Left mouse button with path left button mouse. And the last one, right mouse button with path right button mouse. Remember to save the asset so our changes are propagated to the generated C# class. In the draw component data, we want to store references and parameters of the draw system. So it will be manage type. Let's implement IComponentData interface, then create 6 parameters: compute shader, texture, material, draw width, obstacle width to control brush size, and eraser width. Okay, let's go to the draw afferent class and create 6 serialized fields for compute shader, texture, material, draw width, obstacle width, and eraser width. And of course, getters. I forgot to add namespace in both scripts, so let's correct this. Then create the drawBaker class, and inside the bake method, write getEntity with transferUsageFlag.none. Let's add component object and pass all parameters to the new drawComponentData. That's it. It's time to create our first compute shader in the TaleForge history. We can remove all comments. I will explain everything in a moment. At the top of the file, you can see Pragma kernel CS main. Each kernel tells which function to compile. It is possible to have many kernels, but we only need to add one. So let's rename kernel and function to the following send particles. We can remove any code from the function and leave the result variable. It will come in handy later. We can leave num threads as default, so 8 in one dimension and 8 in the second dimension. In other words, 8 multiplied by 8 equals 64 threads. Okay, let's start with creating all needed variables: float2 pointer position, float draw width, float obstacle width, float eraser width, float time, int texture width, int texture height, and int draw mode. Also, let's rename result to result with small letter. Now let's implement following send particles function. Noteworthy that this compute shaders calculate every pixel of the texture when called. We will call compute shader via JobSystem. We need to get the pixel position, or in other words, pixel ID. So let's create local variable int2 new pixel ID. xid is equal to pointer position.x multiplied by texture width. yid is equal to pointer position y multiplied by texture height. Now we can write const float for new pixel equal to result new pixel ID. It is basically value of the pixel in the color. Const means that this value will not be modified in the future. So something like read-only in the C#. We need to get current pixel ID and value. Const int2 pixel ID equals id.xy and float for pixel equal result pixel ID. Based on this data, we can perform all the necessary operations, of course, transforming the color of the pixel or its position ID accordingly. It's time to check draw mode. If draw mode equals 0, call draw particles with parameters pixel ID, new pixel ID, and new pixel. Else if draw mode equals 1, call draw obstacles with parameters pixel ID, new pixel ID. Else if draw mode equals 2, erase obstacles pixel ID, pixel, new pixel ID. We will implement these methods in a moment, but now let's check if pixel.x is equal to 1 and x equals red color value, so our particle. If so, execute following send logic with two parameters, pixel ID and pixel. Okay, let's start implementing our functions. One important thing, when we use one function in another, the use function must be above the function we are calling from. It is something similar to programming in the old good C language. Void draw particles const int2 pixel ID, const int2 new pixel ID, const float for new pixel. And inside this function, we can write const float this equal distance float2 pixel ID, float2 new pixel ID. You might ask why we need a distance. I want to draw particles in some radius, not single pixel. That's why I check distance of every pixel, and if distance is bigger than draw width, simply return. But otherwise, if this pixel is empty, I can assign red color to the result pixel ID element. Of course, let's implement bool isEmptyPixel function with parameter const float for pixel. This function is really simple. Just return true if conditions are satisfied. Pixel.x and pixel.y equal to 0. We can also create the function bool isOfSequ const float for pixel with return pixel y equals 1 because we will need this function soon. Okay, now it's time to implement draw obstacles. Create parameters const int2 pixel ID, const int2 new pixel ID. Again, we can check distance, and if distance value is smaller than obstacle width, we spawn obstacle, so result is equal to green color. Next, let's create erase obstacles, this time with parameters const int2 pixel ID, float for pixel, and const int2 new pixel ID. This function also checks if distance is greater than eraser width. If so, return. Otherwise, if it's obstacle pixel, set pixel to black. Okay, it's time to implement void function. Execute following sand logic. int2 pixel ID, const float for pixel. First of all, we want to set the direction to int2 0 minus 1, because the particles need to fall down. Result pixel ID is equal to pixel ID plus direction. In turn, result pixel is set to result at result pixel ID index. Then we want to check if result pixel, so pixel below current pixel, is occupied by particle or obstacle. If so, we set the direction.x to pseudo-random number -1 or 1. Unfortunately, we don't have functions to randomize numbers, so it's good time to introduce hash functions, which lets you generate pseudo-random values. In this field, I found great page, shadertoy.com, where are a lot of useful hash functions ready to go. Okay, so let's search for random and select hash without sign implementation. Then go to the common tab, search for the hash 1, 2, and copy paste to our code. Now let's modify vec2p to const float to p2 in the parameters. Change all vec2 and vec3 to the float2 and float3. Don't forget to modify frag to the frag. Let's add summary. In the brief, we can add source to the hash function. In the param section, p2, float2, parameter. And in the return section, pseudo-random number. Great, let's back to the direction x, assign sign, hash 1, 2, float2, pixel ID, plus time, minus half, so we get the range from -half to half. Then assign result pixel ID and result pixel in the same way as before. If result pixel is empty, we can write set pixel and pass 3 parameters, pixel ID, pixel, and result pixel ID. Then return. So let's implement the setResult function. It is a void function in which we set result pixel to pixel value, in our case red color, and reset previous pixel location to the color black. Okay, back to the execute function. Let's write direction.x equal minus direction.x because I want to check opposite side. Assign pixel ID plus direction to the result pixel ID and result at the result pixel ID index to the result pixel. Again, we check if result pixel is empty, and if so, set result. Of course, pass necessary parameters. This way, we check both sides of the slope. That's it for the compute shader. Before we move on, I would like to invite you to support us on Patreon. Even a small contribution will help to develop the channel and the quality of the content present. Link in the description. This system is responsible for communication between ECS input system and compute shader. First of all, let's add partial keyword and inherit from SystemBase. Remember to implement missing method. Next, add update in group type of simulation system group attribute, and then we need to add private static read only properties for compute shader. So let's create draw mode ID, pointer position ID, time ID, base map ID, result ID, draw width ID, obstacle width ID, eraser width ID, texture width ID, and texture height ID. We can also create two needed variables, private vector to in, thread groups, vector to in 0. This parameter is necessary to dispatch execute compute shader, and private int kernel. First of all, create method which will execute shader logic. So let's write public void execute compute shader with three parameters: compute shader, pointer position, and draw input mode. And pass parameters to shader via setIn draw mode ID. We need to modify draw input mode, so let's open draw input mode and change class to enum. We need 4 states: none, which is basically default mode in the draw input system logic, draw particles, draw obstacles, and erase obstacles, which allows us to react to the pointer position and execute compute shader depending on the state. Okay, let's back to draw system and fix variable name. Then set vector pointer position ID, set float time ID, and at the end call our execute compute shader.dispatch kernel threadgroups.x threadgroups.y and 1, because we don't use z dimension. Let's implement onCreate method with require for update draw component data. Then create onStartRunning, where we assign system API.manage_API.getSingleton draw component data to the draw component data. Next, cache draw component data.texture to the initial texture local variable. Let's create size variable and assign it to the new vector to in with texture width and height. Also cache compute shader from draw component data. Finally, find kernel by name, falling send particles. Now we need to create a render texture for compute shader to operate on. So let's write var render texture create render texture size. Add private render texture create render texture vector to int size method, and inside it var render texture equal new render texture size x, size y 0, set wrap mode to clamp, filter mode to point, and enable random write to true. Call render texture.create and return render texture. Now, important thing to do, we need to call graphics.bleed initial texture render texture, which use a shader to copy the pixel data from a texture into a render texture. It's time to set texture on the material, pass base map ID, and render texture. We need to do the same thing in the compute shader, but with the kernel, result ID, and render texture parameters. Then pass all the necessary parameters, it as draw width, obstacle width, eraser width, texture height to the compute shader, so that it is correctly configured. Last thing to do, we need to get kernel thread group sizes. These parameters are necessary to dispatch shader. Let's divide texture size by thread group size. Okay, it's time to handle input. First of all, add parser keyword and inherit from the SystemBase. Of course, implement missing methods. Next, add attribute to the class, update in group type of presentation system group. In this class, we need to create draw map actions so we can subscribe to the events. So let's add private draw input controls draw map actions variable. We also need to call the execute compute shader method from draw system. What's more, it is necessary to make calculations in relation to the camera, especially the screen point to ray and world to viewport point functions. So we'll need to prepare variables for camera and collision filter. Okay, it's time to create new method, protected override void onCreate, in which we write draw input controls, enable input, and cache draw map actions. Add require for update draw component data and physics word singleton. And now let's create onStart running method. Here, get existing system manage draw system, cache camera.main, and prepare collision filter, which will allow to interact with any colliders. Then, in the onUpdate method, let's get singleton, draw component data, and cache collision word from the physics word singleton. Let's create a local variable, draw input mode equal to none. If draw map actions left mouse button is pressed, assign draw input mode, draw particles to the draw input mode. As if draw map actions right mouse button is pressed, assign draw input mode, draw obstacles to the draw input mode. As if draw map actions .space is pressed, assign draw input mode erase obstacles to the draw input mode. Then we need to get pointer position in relation to the texture coordinates. So let's create private vector 2, get pointer position collision word method, and inside it, read pointer position value vector 2 from pointer position action. Next, ray equal to camera screen point to ray pointer position. We want to detect the ECS collision, so we can't use physics raycast, and instead we need to prepare raycast input variable. Start is equal to the ray origin, and is equal to the ray.origin plus ray.direction, and filter is the collision filter. Now, if negate collision word.cast ray input out var hit, so we don't detect collision, let's return vector2.0. Otherwise, we will return camera.word to viewport point hit position. As I said before, I will use viewport calculation to get the mouse position in relation to the texture UV positions, basically simplifying the process to the needs of the tutorial. Last thing to do, let's call drawSystem.executeComputeShader and pass parameters. DrawComponentData.computeShader, pointer position, draw input mode. Great, we handled the input controls. Okay, so let's go back to Unity, wait for the compilation process to finish, then select Draw Component in the ECS subscene and pass Compute Shader, Texture, and Material References. Based on my texture size and experiments, I decided to set Draw Width to 6, Obstacle Width to 10, and Eraser Width to 20. Okay, so let's test everything out, hit play, and as you can see, something is not right. There is a problem with the compute shader because our sand is not falling. Aha! Here's a problem with pixel ID, so let's change it to pixel. Okay, let's try again. Hit play and let's have some fun with our newly created compute shader. Fantastic! Well done!
Hello TaleForgers, in this video I want to show you how I implemented 10,000 skin mesh renderers using Rukhanka VContainer, Polyview and a few other assets, all in Unity ECS. So let's dive in. First of all, let's review the scene settings. The main camera is configured very basically, with post-processing disabled and a solid color set as the background type. Nothing fancy. I also have an animator added because the camera is animated in the timeline. Next, the directional light. I have increased the intensity to 3 because my scene was very dark, especially at a great distance. I disable shadows for better performance. The event system was created automatically when I created a canvas. Now let's take a look at the canvas. It is overlay canvas with some basic settings for full HD. I created a slider here, importantly, with values ranging from 0 to 10 because I assumed a transition from 0 to 10,000 units in increments of 1000. Of course, whole numbers must be checked. Then I prepared unit text, change font size and write some basic input text. Here we have flow control buttons, dance, idle, and run. I mostly use them for debug purposes to check if animations are working properly. Then I use this logic in the timeline signals. Okay, other things will be discussed later in this video. It's time to implement our animating object prefab. First of all, let's talk about the assets. I use the low poly magician model, which is highly optimized character with an acceptable number of triangles, around 3000. I also use the free low poly human RPG character animation asset for the id and run animations. I would highly recommend it for prototyping. And the last one is human dance animations free, which I obviously use for the dance animation. So let's go to the Unity. First of all, I added animator controller with magician character avatar. Let's have a look at the animator settings. As you can see, I have prepared 3 states, dance, idle, and run. I have connected the transitions and assigned the appropriate transition state between them so that it is possible to move from one state to another. In addition, I have disabled exit time to make the transitions smoother. Later, I will modify the animator parameters from the ECS code using Rukhanka. Okay, let's go back to the animating object. It is important to set calling mode to the cal completely. It is important optimization, which will let us spawn more units. Last thing to do, let's add rig definition affering. It is a Rukhanka class which will allow us to configure animation and parse it from mono to ECS world. Here we also want to optimize animations. Let's disable built-in movement and set animation engine to GPU. This will significantly improve the game's performance. Also, let's set bone entity stripping mode to automatic. It will destroy any unnecessary bones and improve performance, because we'll have less entities in the subscene. Alright, we set up animations, now it's time to optimize the mesh. For this purpose, I use the polyview package, which allows us to significantly reduce the number of triangles used in the model without distorting the character itself. So let's select the Consider Children option, as our magician model is lower in the hierarchy. As you can see, with Polyview, I can configure automatic LOD and immediately perform optimization on the mesh for specific groups. I created 3 levels here with the specific parameters, taking care to preserve borders, UV seams, rigid curvature, use edge sort, and recalculate normals. This allowed me to perform satisfactory optimization without distorting the model. In result, I achieved 1.1 million triangles for 10,000 skin mesh renderers. After creating the LOD, a polyview object was created. If we leave it in this form, our performance will suffer, because all these objects will be converted to entities. Therefore, let's use the baking only entity offering component on this group, as it will significantly improve performance. In my case, this resulted in a 50% performance gain. A lot of calculation on ECS local transforms were eliminated this way. While we are on the subject of optimization, let's move on to mobile RP asset. Here, I disable HDR and reduce the render scale to 0.8. In addition, I enabled the Fidelity FX upscaling filter so that the quality of the displayed image would not suffer. The last thing I had to do was create the Rukhanka deformation lead shader. Deformation modules are necessary for skin and mesh renderers to work properly in ECS. The flow is as follows. I copied the original materials and added the part concerning Rukhanka. I have to add Rukhanka deformation group and inside it create the format mesh index and deformation params for motion vectors with hybrid per instance selected. Here I also added a simple color multiplication so that I could modify it from the editor just like the original material. And I checked allow material override. Fortunately, nothing complicated. I did the same in the second material. Finally, we have our prefab prepared. This is time for swim.
Bonjour, mes amis.
Let's start with Unit Spawner component data, which will contain spawn related data. It is a simple struct that stores entity prefab, a bool flag spawn, and int units to spawn. Of course, it implements the IComponentData interface. Next, I have prepared unit spawner offering, the purpose of which is to convert mono prefab to ECS via unit spawner baker. In baker, I mark the entity as renderable, will not be moving it, so there is no need to use dynamic. I also prepared an enum called Rukhanka Showcase Animation State with 4 states: None, Dance, Idle, and Run. We'll need it in a moment in component data. Next, I created a structure that stores information about the currently playing animation, Unit Animation Component Data, with a public field called Rukhanka Showcase Animation State. This component should be baked, that's why I prepared Unit Animation Offering and Baker, so just call add component and set the state to none. Last iComponent to create is Unit Component Data with 2 parameters, public Rukhanka Showcase Animation State and Fast Animator parameter, so our current animation state and animator parameter. We created all these classes so that we could, first of all, instantiate characters and secondly, animate them using Rukhanka. As you can see, I created unit spawner system. This ISystem is marked as Bell's compile. We don't use any managed types. In onCreate, I need to assign unit query so that I can destroy old entities when spawning new ones. I also need to add a require for an update for both our singleton unit spawner component data and EntityCommandBuffer simulation group. In onUpdate, I call systemapi.getSingleton unit spawner component data, and if the spawn flag is not set, I terminate the operation. However, when the spawn flag is true, I change its status to false and continue executing the code. Also, I get EntityCommandBuffer, of course, as ParallelWriter. If Unity query is not empty, I clear the old entity using unit destroy job. It is important to pass unit query because we want to do operations only on the units. Of course, I use schedule parallel. Also, I call jobHandle.complete to wait for the job finish. Let's have a look at job implementation. I am simply destroying entity via ECB ParallelWriter with parameters sort key and entity. Okay, let's go back to the onUpdate method. If units to spawn equals 0, let's return. Now I use a syntax that is highly efficient. Using var entities equals new native array entity unit spawner component data.units to spawn allocator.temp job. Now I can refer directly to the state.entityManager.instantiate, pass the prefab and the array, and spawn as many objects as I need in a single operation. Next, I create a new job, new animating object configuration job, and pass square from the number of units, entities, and ECB ParallelWriter. In this case, I use IJobParallel4, so I have to pass the array length, batch count, and state.dependency. Finally, I wait for the operation to complete. Here I have getEntityCommandBuffer code, in this case with ParallelWriter. Okay, let's have a look at the animating object configuration job. As I said, it is IJobParallel4, so I had to implement public void execute int index. It is important to note that entities need to be marked with read-only attribute because we will not modify them in the job. Inside job, I use simple indexing logic to get units in square, with a small shift, but it doesn't matter for showcase. Next, let's add a new unit component data with an iLoop parameter and set local transfer component from our entities array at a position of a new float x, 0, z multiplied by 2. Multiplying by 2 will give us some space between spawned entities. That's it. It's time to implement our unit animation system. Here we need to create unit query and fast animator parameters for dance, idle, and run. Of course, build unit query in the onCreate, as well as add require for update for necessary component data. Next, in the onUpdate, we want to check if our state is none. If so, return. So we can switch expression animator parameter. Depending on the status, we return the right fast animator parameter. Then let's create new unit animation job, pass state and fast animator parameter. Don't forget to pass ECB ParallelWriter. At the end of this method, we want to reset animation state to none, so system will not be updated any longer. In the unit animation job, in the execute method, I added animator parameters aspect, which is our most important element which will allow us to manage our animation. If the current animation state is not known, set the bool parameter to false for the previously played animation. Then set the current animation to play with the true parameter and assign the UnitComponentData parameters. At the end, remember to set component via ECB ParallelWriter. Okay, so it's time to create our messages. Rukhanka showcase animation message with parameter Rukhanka showcase animation state and Rukhanka showcase spawn message with int units to spawn. So let's implement our communication. In the Rukhanka showcase system, we mainly use VContainer, which allow us to implement subscribers to previously created messages. Of course, this requires communication to take place at the managed level, hence SystemBase. I use disable auto creation attribute to manually register the system and inject dependencies. I will skip the full explanation of the VContainer subscribers and also publishers which are later in the video. I have a video on the channel that explains this, link in the description. So I will go straight to the handlers. In the first handler, we need to change animation state and set singleton when event occurs. In the second one, we need to set spawn flag to true and assign units to spawn to the component data. Then also call setSingleton. And that's it. Finally, we can move to the Rukhanka showcase model, which mostly have serialized fields and getters. Inside it, I have put custom public event action slider pointer up. This event is invoked in the slider pointer up event trigger method, which is used by event trigger in the Unity editor. I didn't want every slider movement to cause a state change, so the entities are only destroyed and spawned when the slider is released. So pointer up. Great, so let's go to the Rukhanka showcase service. This class has two publishers for our messages, and also some public methods. Change state, which publish Rukhanka showcase animation message with new state. Calculate units with the following input parameters, a float value and an int slider base value, so we can calculate how many units need to be spawned. Set unit text, I think this is self-explanatory, and spawn units, which publish spawn message with numbers of units to spawn. So we have our logic, our data. Now we need to communicate it all. In the Rukhanka showcase presenter class, which implement IInitiateBoo and IDisposable interfaces, we have to prepare constructor for injecting service and model classes. In the initialize and dispose methods, we want to add and remove listeners. Also, during the initialization phase, we want to set unit text to 0. So let's have a look at the methods. Dance, iGlue, and run are very straightforward methods. Just call change state and pass right parameters. Set unit text reacts to change in the slider. With each change, the units must be recalculated and the view updated. The spawn unit function is executed on pointer up, spawning the required number of units according to the value set on the slider. Finally, we can move to the Rukhanka showcase lifetime scope, where registration magic occurs. So, as usual, we register the service as scope, the presenter with entry point for interfaces, and the component based on getComponent. Finally, we must remember to register the Rukhanka showcase system in default world, so that we can inject dependencies. At the end, let's change LOD group.crossFade animation duration to 0.3. The last class is for timeline. It allows us to handle custom actions. I will scroll slowly so you can see logic inside it. However, it is nothing fancy. I will leave it as it is, but the word debug doesn't fit in this context. Originally, this class was supposed to do something else, so its name could be Refactor to simply Timeline Controller. It's time to return to Unity. In Rukhanka Showcase Scope, I added two scripts, Model and Scope. In the model, I moved the references to our buttons, slider, and text, and set the base value for the slider to 1000. Below, I added the script necessary for communication with timeline, debug timeline controller, with a reference to the camera and a black target color. At the very bottom, we can see signal receiver, which was created after creating signal emitters in timeline. It is a component responsible for listening to signals and executing our custom logic. To optimize animation, I created an animation frustum calling object and added the animation calling config component provided by Rukhanka. Animation calculation can be disabled for the entities whose renderers are not visible to the camera. Quite a useful feature, right? Okay, it's time to discuss Rukhanka Showcase Subscene. I created two objects, Unit Spawner, in which I attach Unit Spawner offering plus pass animating object, and Unit Animation, where I added Unit Animation offering component. Next, as you can see, I created a playable director that automatically plays on awake with the wrap mode set to hold. Okay, so let's open it in the timeline. I would like to tell you a little more about it. I perform most of the operations on the camera, changing its position and rotation. As you can see, there are quite a few keys here that contains information about the current data. Similar in the directional light, we have a rotation. I changed the angle to better illuminate the characters on the scene. I also prepare some signal emitters, so I can invoke custom logic during timeline sequence. It allows me to change slider value, so spawn more units, change background color, or change animation state. And it's also simple. Just select reference, our timeline script, choose method and pass parameter if necessary. Okay, it's time to show, once more, the final result. Enjoy! Hello TaleForgers! Thanks to the Real Peter 226 request on Reddit, I will demonstrate randomized animation for 10,000 skin mesh renderers. I made it as simple as possible by only modifying the Unit Animation System class rather than the entire logic. That's how I achieved the desired result the fastest way. So let's get started. First of all, let's create member variable private random from unity.mathematics. We need to assign it in the onCreate. Random equals to the new random uint unity engine.random.range 1 int.maxValue. In the unit animation job, let's remove animation state and animator parameter and add public fields, random, dense fast animator parameter, idle fast animator parameter, and run fast animator parameter. Then pass all necessary parameters to the unit animation job, so random and 3 passed animator parameters. We want to implement getRandomState method, which return Rukhanka showcase animation state. This method is burstable. Let's write int value equals random.nextInt 1, 4, so 1 to 3 numbers, and return casted Rukhanka showcase animation state value. Now cut animator parameter switch expression and paste it in the job. Fix animation state to the random state and fast animator parameters calls. Great, it's time to go to the Unity editor, wait for compilation process to finish. Current idle animations is not so well visible, so let's modify it in the animating object controller. I choose jump animation just for the showcase. It's important to enable loop time in the animation settings. Don't forget to apply changes. Also, let's modify run to the roll forward. Remember to modify loop time also. So let's play. As you can see, every single animation is randomized. Enjoy! I would like to invite you to support us on the Patreon, where you can get the exclusive code, all models, materials or code used in the series, and access to early available content. Link in the description. Thank you for your time, I'm glad you are with us and our community is growing. See you soon in the next video.